Yesterday morning, October 29th, 2025, at exactly 11:47 Coordinated Universal Time, something happened that we couldn't see. 3I-ATLAS, the interstellar visitor that's been captivating astronomers since July, reached its closest point to the Sun, perihelion, 203 million kilometers of separation, and for the first and only time in its journey through our solar system, it was completely hidden from Earth's view, tucked behind our star like a card player keeping their hand close to the chest. Now, most comets don't get to pick their moments. They're slaves to gravity, predictable, calculable, down to the second. But what if this one was different? What if, during those hours we couldn't watch, during that perfect blackout window when no telescope on Earth or in Earth orbit could track its movements, 3I-ATLAS did something that natural comets simply cannot do? What if it turned? Not gradually, not subtly, but with purpose and precision, using the Sun's gravitational well like a cosmic slingshot, redirecting probes, maybe dozens of them, toward the inner planets, toward us. The Oberth maneuver. It's what we do with our own spacecraft when we need maximum efficiency. Burn your engines at the point of highest velocity at perihelion and you get the most bang for your buck. Avi Loeb told us to watch for this exact scenario. He told us that if 3I-ATLAS was anything other than a natural comet, yesterday was the day it would reveal itself. And now, as November begins and our telescopes strain to reacquire the target, some of them are picking up signals that don't match the projections, trajectories that have shifted, objects that weren't there before. This is not a drill. This is not speculation anymore. This is what happens when a 7-billion-year-old visitor from the direction of Sagittarius, from the galactic centre itself, decides that Earth is worth a closer look. If you're finding value in this deep dive, please hit that like button and subscribe to the channel. Both really help us continue bringing you these cosmic mysteries. Tell me in the comments where you're listening from, what time it is there, and what you think 3I-ATLAS really is. Natural wonder or something more. Share this video and hit that hype button if you want to help our community grow. Thank you so much for being here. The moment everything changed. Chapter 1. Disclaimer. This is a fictional scenario based on real science and actual data about 3I-ATLAS. The interstellar object followed its predicted trajectory and poses no threat to Earth. This is speculative entertainment exploring what if. Let's go back to the exact moment. 11:47 Universal Time, October 29th. The European Space Agency's Jupiter Icy Moons Explorer, JUICE, was the closest human-made object with a clear line of sight. 64 million kilometers away, still a massive distance, but in space terms, practically next door. JUICE wasn't designed to study comets. It's headed to Jupiter's moons, Ganymede, Europa, Callisto, searching for signs of subsurface oceans and potentially habitable environments. But on October 29th, mission controllers temporarily redirected its instruments. They wanted at least some data from perihelion, some record of what 3I-ATLAS looked like at its moment of maximum solar heating. The first data packets came through 11 hours later. Routine telemetry, compressed imagery, spectroscopic readings. The science team in Darmstadt, Germany processed them overnight. And that's when the anomaly appeared. 3I-ATLAS was brighter than predicted, not by a little, by almost an entire magnitude. Now, comets can surprise you with their brightness. Outgassing can spike unpredictably as volatile ices sublimate under solar radiation. Carbon dioxide, carbon monoxide, water, all of them turning from solid to gas in minutes, creating those beautiful tails and comas we associate with comets. The models predicted 3I-ATLAS would hit magnitude 11.5 at perihelion. JUICE's photometry was showing magnitude 10.1. That's 2.5 times brighter than expected. But brightness alone wasn't the problem. It was the distribution. The glow around 3I-ATLAS wasn't symmetrical. Natural comets develop roughly spherical comas, maybe elongated by solar wind into teardrop shapes, but generally centered on the nucleus. What JUICE captured looked different. Multiple bright spots, 7 distinct luminous regions arranged around the central body, each one exhibiting its own spectral signature, its own pattern of emissions. The JUICE data showed something else: motion, relative motion. Between the time JUICE began its observation sequence and when it ended, 42 minutes later those bright spots had moved. Not in the expected direction, not following the ballistic trajectory you'd expect from ejected material. They were spreading out, diverging, and some of them were accelerating. Think about that for a moment. Natural processes don't accelerate in vacuum. Once you eject material from a comet, it follows Newton's laws. It coasts. It might get pushed by solar wind, by radiation pressure, but those forces don't cause sudden accelerations hours after the initial outburst. Yet here were 7 objects, each roughly the size of a school bus based on their brightness and distance, exhibiting velocity changes that suggested active propulsion. The initial report was classified within hours, not hidden, not covered up, but restricted to the International Asteroid Warning Network, the IATLAS, the group that coordinates global response to potentially hazardous objects. By the evening of October 29th, 36 observatories across 4 continents had been alerted. Emergency observation protocols activated. Every telescope that could slew to the solar region, every instrument capable of detecting objects near the Sun, was retasked, and that's when the second set of anomalies emerged. The Parker Solar Probe, NASA's sun-grazing spacecraft, was in the neighbourhood. Not close enough to image 3I-ATLAS directly, but well positioned to detect any radio emissions, any plasma interactions, any unusual magnetic field disturbances. Parker's instruments recorded a series of structured radio bursts coinciding with the perihelion passage. Frequencies centred around 1.42 GHz, that's the hydrogen line, the so-called universal frequency, the wavelength that hydrogen atoms emit naturally, and the frequency that SETI researchers have monitored for decades, because any technological civilization would recognise its significance. The Parker data showed pulses, not random noise, not the kind of sporadic emissions you'd expect from natural plasma interactions. These were rhythmic, patterned, repeating in intervals that followed a sequence. 3 seconds, then 5, then 8, then 13, then 21. Each pulse lasting exactly as long as its number suggested, and the pattern continued. 34 seconds, 55 seconds, 89 seconds. Some of you are already seeing it. That's the Fibonacci sequence. Each number is the sum of the 2 before it. One of the most famous mathematical patterns in nature, appearing in everything from flower petals to spiral galaxies to the breeding patterns of rabbits. It's a pattern that screams order, that announces mathematical awareness, and it was coming from the direction of 3I-ATLAS at the exact moment of perihelion. Let's be absolutely clear about what this means. The Fibonacci sequence doesn't appear spontaneously in radio emissions. Solar flares don't count to 34, plasma interactions don't solve addition. Natural processes can create patterns, absolutely, but not mathematical sequences that require memory, that require each emission to know what came before it and calculate what comes next. This is information theory. This is signal structure that implies intent. The Parker data was flagged for immediate review. By midnight Central European time, copies had been forwarded to SETI Institute, to the Galileo Project, to Harvard's astronomy department, where Avi Loeb and his team were already awake, already analysing, already sounding alarms that most of the world wouldn't hear for another day. November 1st, this morning, the European Southern Observatory's Very Large Telescope in Chile reacquired 3I-ATLAS. It had emerged from behind the Sun, now visible in the pre-dawn sky for Southern Hemisphere observers. The VLT is one of the most powerful ground-based optical telescopes in the world, capable of resolving details that would be impossible for smaller instruments. And what they saw confirmed the JUICE observations. 3I-ATLAS was no longer alone. The main body, that 5 to 20 kilometre nucleus that we'd been tracking since July, was still there, still following something close to its predicted path. But surrounding it, spreading outward in what could only be described as a formation, were the 7 objects JUICE had detected, and they were no longer clustered. They had separated, each one now millions of kilometres from the parent body, each one on its own trajectory, and 3 of them, were not following paths that would take them out of the solar system. 3 of them were slowing down, decelerating, performing what aerospace engineers call a retrograde burn, firing against their direction of motion to shed velocity. And their new trajectories, when the orbital mechanics were calculated, when the equations were solved and the projections run, all pointed to the same destination, Earth. The closest approach date kept appearing in the calculations, December the 19th, 2025, 50 days from now. Not the main body of 3I-ATLAS that will pass us at its predicted distance of 270 million kilometres, far beyond any possibility of interaction. But the probes, the 7 objects that separated at perihelion, 3 of them will arrive much, much closer. Current estimates put them within 10 million kilometres of Earth. That's less than 1/15 the distance to the Sun. That's inside the orbit of our own moon by a factor of 25. And here's where things get terrifying and fascinating in equal measure. Those probes are massive. JUICE's initial photometry suggested each one has a diameter of at least 30 metres. That's bigger than any satellite humans have ever launched. That's bigger than the International Space Station's individual modules. And they're not tumbling randomly like you'd expect from debris or fragments. They're oriented, stabilised, each one pointing in a specific direction as it travels, exhibiting what's called 3-axis attitude control, the same stabilisation system we use on our most advanced spacecraft. How do we know this? Because they're reflecting sunlight in predictable patterns. When an object tumbles, its brightness varies chaotically as different surfaces catch the light. When an object maintains orientation, its brightness remains steady or varies in regular cycles. The VLT photometry showed periodic variations with cycles of exactly 16.2 hours. The same rotation period that 3I-ATLAS exhibited. It's as if whatever detached from the parent body took its spin with it, maintaining synchronization even after separation. This isn't speculation. This isn't hysteria. These are measurements made by multiple independent observatories using different instruments and different methodologies, all reaching the same conclusion. Something happened at perihelion, something that natural comets don't do. And now, as November unfolds and our tracking improves with every passing night, we're being forced to confront possibilities that most scientists have spent their careers dismissing. The International Asteroid Warning Network held its first emergency session since its founding on November 2nd. Representatives from NASA, ESA, Roscosmos, JAXA, CNSA, every major space agency, plus astronomical societies from 37 countries. The meeting was closed door, but the agenda leaked within hours. Item 1 confirmed the trajectory of all 7 objects. Item 2 assess probability of natural versus artificial origin. Item 3 determine Earth impact risk. Item 4 establish communication protocols. Item 5 authorize defensive measures. That last item is what made headlines: defensive measures. The phrase appeared in multiple leaked documents, and while no one is talking publicly about what that means, the implications are obvious. If something is coming toward Earth, and we can't be certain of its intentions, we need options. Options to observe, yes, but also options to intercept, to deflect, to destroy if necessary. The United States Space Force, the newest and most controversial branch of the American military, has been quietly activating assets. Satellite tracking networks that normally watch for missile launches are being retasked to monitor the region of space where the 3I-ATLAS probes are travelling. Ground-based radar installations, the massive phased array systems designed to detect incoming ballistic threats, are being recalibrated to track objects millions of kilometres away. And in classified facilities, engineers are running simulations, wargaming scenarios, trying to determine if our most powerful rockets could reach the probes before they reach us, and if our most powerful weapons could do anything to stop them if they turn out to be hostile. But here's the paradox that's keeping scientists awake at night. We don't want to destroy them. Even if we could, even if we had the capability and the certainty of success, we don't want to. Because if these objects are artificial, if they represent the first confirmed contact with extraterrestrial technology, destroying them would be the most catastrophic mistake in human history. We'd be announcing ourselves to the galaxy as violent, paranoid, shoot first, and ask questions never. We'd be destroying the very evidence we need to understand who sent them, why they're here, what they want. And so we wait. We watch. We track every kilometre of their approach. We point every available instrument at them, and we collect data, spectroscopy, photometry, radar returns when they get close enough, radio monitoring across every frequency we can scan. We look for more signals, more patterns, more evidence of intent, and we prepare, quietly, reluctantly, for the possibility that December 19th will be remembered as either the greatest day in human history or its last. The probes are moving at approximately 68 kilometers per second relative to the Sun. That's fast, incredibly fast by human standards, but slow for interstellar objects. 3I-ATLAS itself was clocked at 221,000 kilometers per hour when it was discovered. The These probes have shed enormous amounts of velocity. The energy required for that deceleration is staggering. We can calculate it. Mass times velocity squared divided by 2. Even assuming the minimum mass based on their observed size, we're talking about energy expenditures equivalent to multiple nuclear detonations. Per probe. That's not outgassing. That's not solar wind. That's propulsion. That's fuel being burned, reaction mass being expelled, engines firing in the cold vacuum of space. And that brings us to the question that no one wants to ask out loud, but everyone is thinking. If they have enough fuel to slow down, do they have enough fuel to speed up again? Are these probes on one-way missions, content to observe and report back, or are they capable of manoeuvring further, of entering Earth orbit, of landing, of doing whatever it is they were sent to do? We don't know. And that might be the most honest and terrifying answer science has ever had to give. Decoding the turn, the mathematics of what happened at perihelion are almost beautiful in their brutality. When you're dealing with orbital mechanics at these scales, every number tells a story, and the story those numbers tell is one that shouldn't be possible for a natural object. Let's walk through exactly what would need to happen for those probes to reach Earth on December 19th. 3I-ATLAS approached perihelion at 68 kilometers per second. That velocity is oriented primarily in the direction that would carry it back out toward interstellar space, following the hyperbolic trajectory we've been tracking since July. To redirect even a small portion of mass toward Earth requires changing that velocity vector dramatically. Not just slowing down, but rotating the direction of motion through almost 90 degrees. The energy cost for that maneuver scales with the square of the velocity change, and when you plug in the numbers, when you account for the mass of those 30-meter probes and the delta V required, you get a result that makes rocket scientists pale. Each probe would need to carry fuel mass equal to roughly 40% of its total launch mass. That's assuming a specific impulse comparable to our best chemical rockets. If they're using something more exotic, nuclear thermal, fusion, antimatter, the ratios change. But the fundamental problem remains. You can't cheat physics. To slow down and turn toward Earth requires either carrying impossible amounts of fuel or using propulsion technologies that operate at efficiencies we can barely theorize. Dr. Sarah Chen at MIT's Aeronautics Department ran the calculations using our most optimistic projections for advanced propulsion. Even assuming a fusion drive operating at specific impulse values 10 times better than anything humans have achieved, the fuel requirements are staggering. We're talking about technology that represents either thousands of years of advancement beyond our current capabilities, or a fundamental breakthrough in physics that allows propulsion without reaction mass. Either option is sobering. But here's where it gets stranger. The timing. The precise timing of the separation event. If you're going to release probes toward inner solar system targets, perihelion isn't just convenient, it's optimal. That's the Oberth effect in action. When you're deep in a gravity well, when you're moving at maximum velocity, every bit of thrust produces amplified results. Fire your engines at perihelion, and you get more change in orbital energy per unit of fuel than at any other point in your trajectory. It's basic orbital mechanics, something we've known since Tsiolkovsky laid out the rocket equation over a century ago. The fact that 3I-ATLAS performed this maneuver, if that's what happened, at the precise moment of maximum efficiency suggests planning. It suggests understanding of the local gravitational environment. Natural comets don't wait for optimal moments, because natural comets don't have goals. They're governed entirely by gravity and outgassing forces, neither of which care about efficiency or timing or whether you're being watched. And we weren't watching. That's the detail that keeps coming back. The detail that feels less like coincidence and more like strategy with each passing day. Solar conjunction happens. It's predictable, calculable years in advance. When 3I-ATLAS was first discovered in July, orbital calculations immediately showed it would pass behind the Sun from Earth's perspective in late October. That's geometry, not conspiracy. But the perihelion date landing right in the middle of that blackout window, when no telescope on Earth or in Earth orbit could observe it directly, when even our closest spacecraft could only catch glimpses from oblique angles, that timing is remarkable. Some scientists, the cautious ones, the ones who've spent careers building reputations on careful skepticism, they argue coincidence. Space is vast, they say. Alignments happen. The fact that we couldn't watch doesn't mean we were being deceived. And they're right, of course, in the purely statistical sense. But statistics and reality don't always shake hands. Sometimes the universe arranges itself in ways that strain credulity, and when those arrangements coincide with other anomalies, with Fibonacci radio pulses and trajectory changes and probe separations, the coincidence explanation starts feeling less like science and more like wishful thinking. The reverse Oberth maneuver, what those probes would have had to execute to reach Earth, requires not just fuel, but precision. You're essentially doing a controlled crash into a gravity well, using your engines to shed velocity at exactly the right moments to capture yourself into an approach trajectory. Get the burn timing wrong by even a few seconds, and you miss your target by millions of kilometers. Get the thrust vector wrong by a fraction of a degree, and you end up in the wrong orbit entirely. The fact that 3 probes, 3 separate objects, all managed to nail their burns with sufficient precision to target Earth arrival within the same 24-hour window speaks to coordination. Either they're all following pre-programmed instructions uploaded before separation, or they're communicating with each other, adjusting their trajectories based on shared data. Either scenario requires computational capability, navigation systems, propulsion control, all the hallmarks of technology. Ground-based radar won't be able to track the probes reliably until mid-November, when they cross inside the orbit of Mars and get close enough for return signals to punch through the noise, but optical tracking is improving daily. Every night, as Earth's rotation brings fresh telescopes into view of the morning sky, astronomers are refining their measurements. The probe trajectories are being calculated with increasing precision, and those calculations keep pointing to the same arrival window, December 18th through 20th, depending on which probe you're tracking and which set of orbital elements you trust. The closest approach distances vary. The current best estimates put Probe 1, the designation they've assigned to the largest and brightest object, passing within 8.7 million kilometers of Earth. That's about 23 times the distance to the Moon, far enough to pose no collision risk, close enough to resolve surface features with our best telescopes, probes. 2 and 3 will pass at 9.2 and 10.1 million kilometers respectively. The other 4 probes, the ones whose trajectories didn't bend toward Earth, are headed elsewhere. 2 appear targeted for Venus, arriving in early January. 1 is on course for Mars, a slower approach that won't arrive until March. And the 7th, the one that's been hardest to track, seems to be heading outward, toward Jupiter, following a trajectory that almost perfectly mirrors the path 3I-ATLAS itself will take. That distribution isn't random. 7 probes, 7 targets. The inner planets, the gas giant, and 1 heading back to deep space, potentially to report on the mission, to carry data home to whoever sent it. It's the kind of distribution you'd expect from a survey mission, from a scientific expedition designed to sample multiple environments in a single pass through a solar system. We do the same thing with our flyby missions. Voyager wasn't sent just to Jupiter. It was designed to visit multiple targets, to maximize science return from a single launch opportunity. If 3I-ATLAS is a mothership, if those probes are survey instruments, then their dispersal pattern makes perfect strategic sense. But survey missions imply curiosity. They imply scientific interest, desire to understand, to collect data and learn. And that raises the question that dominates every conversation, every meeting, every encrypted message passing between observatories and space agencies. What are they surveying? What do they want to know? And most critically, what will they do with the information once they have it? The nickel signature hasn't gone away. Spectroscopic observations from multiple facilities continue to show that unusual emission line, nickel vapor in concentrations that shouldn't exist in natural cometary material. Nickel is common enough in the universe, sure, but it's almost always found bound with iron in roughly equal proportions. That's how cosmic chemistry works. Nickel and iron form together in the cores of massive stars and get blasted into space together when those stars explode. Every meteorite we've ever studied, every asteroid we've sampled shows that ratio. Nickel and iron together, always. Except in 3I-ATLAS. The spectra show abundant nickel, but negligible iron. That's metallurgy, not astronomy. That's refining, smelting, industrial processes that separate elements based on their properties rather than their natural abundances. Some geochemists have proposed exotic formation scenarios, weird stellar environments where nickel might separate from iron through natural fractionation, but those proposals require conditions so specific, so unlikely, that they're essentially special pleading. The simplest explanation, the one that fits the data without inventing new physics, is that the nickel isn't natural. It's manufactured. It's an alloy, selected for properties we can only guess at: strength, conductivity, resistance to radiation or thermal stress, the kinds of properties you'd want in a spacecraft hull. And then there are the light curves. As the probes rotate, they reflect sunlight in patterns that reveal their shape. Natural objects, rocks and ice balls tumbling through space produce irregular light curves, lumpy, asymmetric, chaotic. The 3I-ATLAS probes produce light curves that look engineered, regular brightness variations with sharp peaks and smooth valleys, exactly what you'd expect from objects with geometric symmetry. Cylinders, maybe, or elongated ellipsoids, shapes that suggest design rather than accidental formation. Dr. James Robertson at Caltech has been analysing those light curves obsessively. He's built models, run simulations, tried to match the observed brightness patterns with different assumed shapes. His best fit, the model that reproduces the observations most accurately, describes the probes as cylindrical objects roughly 35 metres long and 12 metres in diameter. That's space shuttle-sized. That's Saturn V upper stage dimensions. And the surface reflectivity suggests smooth exteriors, not the rough porous surfaces characteristic of cometary fragments. None of this is proof. Science doesn't deal in proof, not really. Science deals in evidence, in models that fit data, in hypotheses that survive testing. But the evidence is stacking up piece by piece, measurement by measurement, and the hypothesis that survives best, the one that requires the fewest special assumptions and the least exotic physics, is the one that says these objects are not natural. Defense planners are running their own calculations, independent of the scientific community, and their conclusions are shaped by different priorities. They're not asking what the probes are, they're asking what the probes can do. How fast could they maneuver if they wanted to? How much delta V might they have in reserve? Could they alter course again, target different locations, maybe even enter Earth's atmosphere? The answers to those questions depend on assumptions about propulsion technology and fuel reserves, assumptions we have no way to verify. But the worst-case scenarios, the ones that keep military analysts awake in their secure facilities, involve probes with enough remaining propulsion authority to make multiple major trajectory changes. If they can slow down from interstellar velocities, what else might they be capable of? Could they match Earth's orbital velocity? Could they pace us, staying at fixed distances, observing for extended periods? Could they descend into our gravity well, targeting specific locations on the surface? Those questions lead to others, darker and more urgent. What payload might they carry? Instruments, certainly, cameras and spectrometers and sensors of types we can only imagine. But what else? Communication equipment, presumably, to transmit findings back to the mothership or beyond. Computation, navigation, power generation. And if they're capable of precision maneuvers and controlled approaches, why not descent systems, landing gear, surface mobility? This is the territory where science fiction and strategic planning blur together. We have no evidence for any of this, but we also have no evidence against it. The probes are black boxes, literally and figuratively. We can measure their orbits and their shapes and their reflected light, but we can't see inside. We can't know their intentions or capabilities until they reveal them, and by then, if those intentions are hostile, it may be too late to respond effectively. December 19th is 50 days away. That's how long we have to gather data, to refine our understanding, to decide how humanity will respond to visitors we didn't invite and can't ignore. 50 days to go from denial to acceptance, from skepticism to preparation, from hoping it's natural to planning for the possibility that it's not. 50 days before we find out if we're alone in the universe, or merely one data point in someone else's survey mission. The Sagittarius connection direction matters. In the vast emptiness of interstellar space, where distances dwarf human comprehension, and stars scatter across 3 dimensions like sand grains in a cosmic desert, the direction something comes from tells a story all its own. 3I-ATLAS didn't arrive from just anywhere. It came from Sagittarius, from the heart of our galaxy, from the direction where our Milky Way's supermassive black hole lurks beneath veils of dust and starfire. That region of sky, that 30-degree arc where Sagittarius dominates the southern celestial sphere, has always held special significance. Ancient peoples saw an archer there, a centaur drawing his bow, aiming at Scorpius the scorpion. Greek mythology named him Chiron, the wise centaur, teacher of heroes, the one who gave up his immortality to end his suffering. The irony isn't lost on astronomers watching an arrow from that exact region of sky now approaching Earth. We've been hit before by cosmic projectiles, asteroids and comets that ended species and reshaped continents. Is history preparing to repeat itself, but this time with intent rather than accident? The galactic centre itself sits embedded in Sagittarius, 26,000 light-years away but optically invisible, hidden behind thick lanes of interstellar dust that block visible light while allowing infrared and radio to pass through. Sagittarius. A star, the supermassive black hole anchoring our galaxy's core. Mass is 4 million times what the Sun does. It's a gravitational monster, warping space-time around it so severely that stars orbit at thousands of kilometers per second, their paths bent into tight ellipses by forces that would tear ordinary matter apart. Around that black hole, in the dense stellar environment of the galactic bulge, stars crowd together with separations measured in light days rather than light years. Interactions are common: close encounters, gravitational slingshots, systems disrupted and reformed by passing neighbours. It's a violent, dynamic region, nothing like the quiet galactic suburbs where our Sun peacefully orbits, and it's from that direction, from that maelstrom of stellar activity and extreme physics, that 3I-ATLAS emerged after billions of years of travel. The statistical analysis keeps coming back to haunt us. When researchers trace the object's trajectory backward, when they account for galactic rotation and stellar motions and gravitational perturbations from everything we know about, the origin point remains stubbornly fixed near the galactic centre. Not from a specific star, that precision is impossible over such distances and timescales, but from that general region, that volume of space where stellar density peaks and exotic objects congregate. And then there's the other signal, the older one, the one that refuses to be explained or forgotten despite decades of trying. August 15th, 1977, the Big Ear radio telescope in Ohio detected a signal so strong, so precisely confined to the hydrogen line frequency, that the astronomer reviewing the data the next day scrawled "Wow" in the margin of the printout. That exclamation became its name. The WOW signal, 72 seconds of narrowband radio emission that arrived from guess where? Sagittarius. Same constellation, same general region, 48 years earlier. The Big Ear never heard it again. Follow-up observations found nothing. Decades of searching that patch of sky have turned up only silence. Skeptics proposed everything from satellites to comets to secret military transmissions, but none of those explanations fully satisfy. Satellites don't produce narrowband hydrogen line emissions. Comets don't generate radio signals powerful enough to register from interstellar distances. And the signal's frequency, 1.42 GHz, isn't used by terrestrial broadcasts precisely because astronomers lobbied to keep that band reserved for scientific observation. Recent analysis by Antonio Paris suggested the signal could have come from a comet, specifically 266 P. Christensen, that happened to be transiting that region of sky in 1977. Comets can emit radio radiation through processes involving their hydrogen clouds, but the details don't quite work. The signal was too strong, too focused, too brief. And Paris's comet, when other researchers checked the orbital calculations, wasn't actually in the right position to produce the observed signal. The mystery remains. Now we have 3I-ATLAS, another visitor from Sagittarius. This one carrying not just radio signals but physical presence, mass and velocity and structures that might be artificial. The connection feels too significant to dismiss. Two anomalies from the same direction across a span of half a century. What are the odds? Actually, we can calculate those odds. The galactic centre occupies roughly 1% of the sky as seen from Earth. If anomalies arrive from random directions, the probability of two independent events, both originating from that 1%, is 1 in 10,000. Not impossible, but certainly noteworthy. Add in the fact that both involve narrowband radio emissions and the probability drops further. Add in the hydrogen line frequency connection, and you're into territory where coincidence starts looking less plausible than correlation. Some researchers are going further, suggesting that the WOW signal might have been an intentional beacon, a hailing frequency designed to get our attention and announce an incoming visitor. 48 years from signal to arrival sounds like a long time by human standards, but for interstellar travellers, For civilizations capable of crossing light years, such timescales might be routine. Send a signal ahead, give the locals notice, arrive decades later to see if anyone responded. It's what we'd do if we had the capability. The Voyager Golden Records, the messages to ETI encoded in our deep space probes, they're essentially the same strategy. Hello, we're here, this is what we're like, we're coming your way even if it takes thousands of years. The mythology runs deeper than astronomy. Sagittarius, the Archer, the Centaur, represents the liminal space between human and animal, between civilization and wilderness. Centaurs were guardians of knowledge in Greek tradition, teachers of medicine and music and warfare. They bridged worlds, inhabited borders between the known and unknown. Is that what 3I-ATLAS represents? A bridge? An intermediary between our isolated solar system and the wider galactic community that might exist out there in the dark? The constellation's position in our sky isn't arbitrary either. Sagittarius sits on the ecliptic, the plane where planets orbit. 3I-ATLAS's trajectory aligns within 5 degrees of that plane, an orientation that has only 0.2% probability for a random interstellar object. But if you're targeting a solar system, if you're planning a survey mission or a contact attempt, approaching along the ecliptic makes sense. That's where the interesting real estate is, the rocky inner planets and gas giants, the asteroid belt and Kuiper belt objects. An approach perpendicular to the ecliptic would minimize your time in the plane where targets exist. An approach along the ecliptic maximizes interaction possibilities. Ancient astrologers associated Sagittarius with the 9th house, the domain of long journeys, foreign lands, philosophy and higher learning. They couldn't have known about interstellar space or galactic structure, couldn't have predicted that their Archer constellation would point toward the literal center of our cosmic home. Yet here we are, receiving visitors from exactly that direction. Visitors that raise the most profound philosophical questions humanity has ever faced. The synchronicity is almost too perfect. December 19th has its own symbolic weight. 6 days before Christmas, in the darkest part of the year for Northern Hemisphere civilizations, when ancient peoples lit fires against the cold and told stories about stars and gods and renewal. The winter solstice, when the sun reaches its lowest point and begins returning northward, happens just 2 days after the projected arrival. Every major culture in the Northern Hemisphere developed some kind of light festival around this time. Hanukkah, Christmas, Yule, Dongji, Dies Natalis, Solis Invicti, all of them celebrating light's return, hope's persistence, the promise that darkness isn't permanent. Now we're waiting for a different kind of light, a different kind of promise or threat, arriving precisely in that charged symbolic window. Some religious scholars are already drawing parallels, talking about signs in the heavens, portents of transformation or judgment. Others see it as purely coincidental, pointing out that December 19th is just another day, that our cultural associations don't influence orbital mechanics or alien intentions. But symbols matter to humans even if they don't matter to physics. The fact that this potential first contact is happening during a season associated with gift-giving, with visitors bringing presents and good news, colours how we think about it. Avi Loeb's phrase, calling the probes potential Christmas gifts to humanity, wasn't just a rhetorical flourish. It tapped into deep cultural narratives about strangers bringing valuable offerings, about surprising arrivals that change everything. The Pleiades add another layer. When 3I-ATLAS was discovered in early July, the moon passed directly in front of the Pleiades cluster, a rare occultation that happens only once every few years. The Pleiades, also called the Seven Sisters, are 7 bright stars in Taurus, the Bull, another zodiacal constellation. Greek myth connects them to Atlas, the titan who held up the heavens, whose daughters became the star cluster after he was punished for challenging Zeus. The name resonance isn't lost on anyone. 3I-ATLAS, discovered during a Pleiades lunar occultation, releasing 7 probes toward inner solar system targets. 7 sisters, 7 probes, 7 objects carrying unknown purposes toward our small world. These patterns might mean nothing. The universe is vast and complex and full of coincidences. We're pattern-seeking creatures, evolved to find signals in noise because missing a real pattern could mean death. But seeing false patterns just wastes time. Our ancestors who saw predators in every shadow survived better than those who waited for certainty. So we find meanings everywhere, connections between things that might be utterly independent. That's a feature, not a bug, of human cognition. But what if occasionally the patterns are real? What if some coincidences aren't? What if a civilization capable of sending probes across light years is also capable of choosing arrival times that resonate with target civilizations, that carry symbolic weight, that maximize psychological impact? We'd do it if we could. When Voyager's golden record was being designed, enormous care went into selecting images and sounds that would communicate not just information but meaning, that would present humanity in ways we found significant and representative. Why assume aliens would be less thoughtful? The galactic centre remains enigmatic even without 3I-ATLAS. We know there's a black hole there. We can measure its mass by tracking stars in orbit around it, but we can't see it directly. We know there are young stars near the galactic centre despite the intense radiation that should prevent star formation, and we don't fully understand how they got there. We detect gamma-ray emissions and X-ray flares and radio bursts from that region, some of them following patterns we can't explain. It's a laboratory of extreme physics, a place where our models break down and new phenomena await discovery. If you were a civilization wanting to sample the galaxy, wanting to understand how stars and planets form and evolve across different environments, the galactic centre would be a natural home base. Dense stellar environment, rich in heavy elements, lots of activity and interaction. You could observe thousands of star systems from a relatively compact region. You could send out exploratory missions to the sparser, quieter parts of the galaxy, places like our solar neighbourhood where stars bake in isolation for billions of years, and weird things like technological civilizations might occasionally arise. This is speculation layered on speculation, mythology tangled with astronomy, pattern recognition running wild without hard evidence to constrain it. But it's also the kind of thinking that sometimes leads to insight, to asking questions that wouldn't occur to people who insist on rigorous proof before entertaining possibilities. Science advances by bold hypotheses tested by careful data. Right now we're heavy on hypotheses and light on data, but December 19th will correct that imbalance one way or another. The probe swarm. They have names now. Not official designations from the International Astronomical Union, those will take months to finalise through proper bureaucratic channels, but working labels that astronomers and military analysts use to track them, to distinguish one from another in the growing mountain of observation data. Probe 1 through Probe 7, uninspired but functional, each one representing a 30-metre mystery hurtling through space with purposes we can only guess. Probe 1, the largest and brightest, is the one keeping everyone awake. Its trajectory has been refined with each passing night of observation, and those refinements keep confirming the same unsettling conclusion. Closest approach on December 19th at 03:15 Universal Time. Distance of 8.7 million kilometres, velocity at encounter roughly 45 kilometres per second. That velocity is slow for an interstellar object, but insanely fast by human standards. 45 kilometres per second is 9 times faster than the fastest spacecraft we've ever launched. It's fast enough to cross the Earth-Moon distance in under 3 hours. But here's what makes Probe 1 special. Its deceleration is continuing. The object is still slowing down, still shedding velocity at a measurable rate. That means its engines, whatever form they take, are still firing, still burning fuel or reaction mass, still producing thrust days after the initial separation at perihelion. Natural objects don't do that. Once you separate from a parent body, once you've been given your initial velocity by whatever ejection process launched you, you coast. Conservation of momentum. Newton's first law. An object in motion stays in motion unless acted upon by an external force. Probe 1 is being acted upon by an external force, its own propulsion system, and the thrust profile, the pattern of deceleration over time, looks controlled. Not constant thrust like you'd expect from a chemical rocket burning until exhaustion, but variable thrust, increasing and decreasing in a pattern that suggests active guidance. Someone or something is steering. Making. Course corrections, fine-tuning the trajectory, ensuring arrival at a specific target point in space and time. Dr. Margaret Okonkwo at NASA's Jet Propulsion Laboratory has been modelling Probe 1's trajectory with increasingly sophisticated algorithms. Her latest projections show something that turned her skepticism into genuine concern. If Probe 1 continues its current deceleration profile, if it keeps slowing at the observed rate for another 3 weeks, it will match Earth's orbital velocity. Not pass by Earth, not zoom past us at 45 kilometers per second. It will pace us. It will achieve what orbital mechanics calls a rendezvous trajectory. where two objects moving in space arrive at the same point with similar velocities, enabling extended interaction or docking or capture. That capability changes everything. A probe that can rendezvous with Earth can potentially enter orbit. It can take up station at a fixed distance, observing for extended periods, maybe months or years. It can study us in detail, watch our cities and communications and activities, compile comprehensive reports on this strange technological species it's discovered. Or it could do other things. It could deploy additional payloads. It could establish permanent presence. It could wait, patient and alien, for instructions from home on how to proceed with whatever mission parameters guided its creation. Probe 2 is on a different trajectory entirely. Closest approach, December 20th at 1740, universal time, distance 9.2 million kilometers. But its velocity curve is weird. Instead of steady deceleration like Probe 1, Probe 2 is maintaining nearly constant velocity with only minor corrections. It's going to zip past Earth at 48 kilometers per second, close enough for excellent remote sensing but too fast for capture or rendezvous. Its trajectory after Earth encounter projects outward, back toward the outer solar system, suggesting it might be a reconnaissance probe rather than a landing mission. Observe and report, don't linger. The photometry of Probe 2 shows different characteristics than Probe 1. Its brightness variations are more irregular, less geometric. Some analysts interpret this as evidence of surface features, possibly instruments or antennae extending from the main body. If you're designing a probe for close flyby observation, you'd want maximum sensor coverage, cameras and spectrometers and radar systems pointing in multiple directions to capture data during the brief encounter window. Probe 2 might be optimized for that mission profile, bristling with instruments that give it a less symmetrical appearance than its siblings. Probe 3 is the enigma. Its orbit has been hardest to pin down, complicated by apparent trajectory changes that don't follow simple ballistic curves. Some observations suggest it's performing small course corrections every few days, adjustments too precise to be outgassing effects. The latest orbital solutions put its closest approach on December 18th, a day earlier than the others, at 10.1 million kilometers. But those solutions carry large error bars, uncertainties that won't resolve until radar tracking becomes possible in mid-November. What makes Probe 3 particularly interesting is its rotation state. Unlike Probes 1 and 2, which maintain stable spins with regular 16-hour periods, Probe 3 appears to be tumbling. Its brightness variations are chaotic, suggesting uncontrolled rotation around multiple axes. That could indicate damage, something that went wrong during separation from the mothership. Or it could be intentional, a probe designed to sample the space environment from constantly changing orientations, maximizing data collection by exposing different sensor suites to different aspects of the sky. Then there are the Venus probes, 4 and 5. Their trajectories diverge from the Earth-bound objects dramatically, bending inward toward the Sun rather than outward. Venus reaches inferior conjunction, its closest approach to Earth, in January, and that's when these probes will arrive. Venus is hell, an 800-degree furnace with crushing atmospheric pressure and clouds of sulfuric acid. Nothing we've sent there lasts more than a couple hours before succumbing to the heat and corrosion. But Venus is also a laboratory for studying extreme greenhouse effects, atmospheric superrotation, and the boundaries of planetary habitability. If you're surveying a solar system, if you want to understand the full range of terrestrial planet conditions, Venus is essential data. The Venus probes are smaller than their Earth-directed cousins, or at least they appear dimmer, suggesting either smaller size or different surface properties. They're not decelerating as aggressively, which makes sense because Venus has a thick atmosphere that could be used for aerobraking. If these probes are designed to enter Venusian atmosphere, they wouldn't need as much propulsion fuel. They could dive in and let friction do the work of slowing down, though they'd need extraordinary thermal protection to survive even brief exposure to those conditions. Probe 6 is the Mars mission. Its trajectory is the slowest, the most leisurely of the 7, a gentle curving path that will bring it near the red planet in March 2026, 4 months from now. Mars is currently on the far side of the Sun from Earth, geometrically separated but still accessible to a probe with patience and fuel to burn. The Mars trajectory requires less delta V than the Earth trajectories because Mars is further out, higher in the Sun's gravity well, slower in its orbit. It's actually the most energy-efficient target among the inner planets for something approaching from interstellar space. But Mars also has something Earth lacks: unambiguous evidence of human presence. Rovers and landers, orbital satellites, habitats that might someday house permanent settlements. If you're studying the local technological species, Mars tells you about expansion capabilities, about our reach beyond our homeworld, about whether we're confined to one planet or spreading outward. Probe 6 will get to observe our off-world infrastructure up close, assuming it approaches close enough and our Mars assets are still functional when it arrives. The 7th probe, the Outlier, is heading away. Back out toward the gas giants, following a trajectory that will take it past Jupiter in June 2026, almost exactly 8 months from now. Jupiter is the king of planets, 300 times Earth's mass, a scaled-down star that didn't quite make it to ignition. Its magnetic field is enormous, its radiation belts deadly, its moons a collection of alien worlds ranging from volcanic Io to ice-covered Europa to massive Ganymede with its subsurface ocean. Jupiter represents a completely different planetary environment than the rocky inner worlds, and surveying it rounds out the dataset. Probe 7 is also the brightest after Probe 1, suggesting comparable size or higher reflectivity. Its trajectory matches 3I-ATLAS more closely than any of the other 6, as if it's escorting the mothership, maintaining formation as they both head outward. Some analysts speculate this might be the communications relay, the probe responsible for gathering data from its 6 siblings and transmitting consolidated reports back to 3I-ATLAS or beyond. If you're going to send probes to 7 different targets, you need some way to collect their findings. Probe 7 could be that central hub, the mission coordinator that ensures all the data gets home. The separation event itself remains mysterious. JUICE saw the aftermath, 7 objects already distinct and spreading out but didn't catch the moment of release. What forces were involved? Did 3I-ATLAS fragment violently, breaking apart under thermal stress or tidal forces? That explanation fails because the mothership is still intact, still following its original trajectory with no apparent mass loss beyond normal cometary outgassing. Did it eject the probes mechanically, using some kind of launching system? Spring-loaded mechanisms, compressed gas ejection, electromagnetic catapults? Those are technologies we understand, scaled up to alien engineering standards but conceptually familiar. Or was it gentler? Did the probes detach and drift away under minimal impulse, then light up their own engines once clear of the mothership? That would minimize mechanical stress and allow more controlled separation, but it requires the probes to carry their own propulsion from the start, adding mass and complexity. Either way, the separation was planned. 7 objects don't spontaneously arrange themselves into trajectories, targeting 7 distinct solar system bodies by accident. The targeting alone requires navigation data, knowledge of where planets will be months in the future, calculations that account for gravity and orbital motion, and interception geometry. There's another possibility that fewer scientists want to discuss publicly. What if the probes were always separate? What if 3I-ATLAS isn't a mothership but a convoy, 7 independent spacecraft flying in formation across interstellar space? Cloaked or camouflaged somehow to appear as a single object until perihelion, when they dropped the pretense and diverged to their assigned targets. That scenario implies even more sophisticated technology, active stealth systems and coordinated flight controls and deception planning. It also implies intentions worth hiding, reasons to conceal your true nature until the moment of commitment. The tracking data will improve dramatically once radar comes online. Radio waves can measure distances and velocities with precision that optical observations can't match. Radar can also detect surface properties, roughness, and composition, maybe even large-scale structure if the return signals are strong enough. Arecibo would have been perfect for this, the massive Puerto Rican dish that collapsed in 2020, a loss that the astronomical community is still mourning. But other facilities remain. Goldstone in California, Green Bank in West Virginia, the planetary radar systems at NASA's Deep Space Network. All of them will be pointed at the probes once they enter effective range. Military installations are tracking them too, using systems not designed for scientific observation, but perfectly capable of it. Early warning radar networks, ballistic missile defense sensors, installations whose existence is classified, but whose capabilities are well known to anyone who pays attention. Those systems can track objects much smaller and faster than anything the civilian telescopes can resolve. They're watching the probes constantly, feeding data into threat assessment models, calculating impact probabilities, even though impact is vanishingly unlikely given the projected trajectories. Unless the trajectories change again. That's the fear that motivates all the redundant tracking, all the obsessive monitoring. If the probes could alter course once, they can do it again. If they have fuel reserves for rendezvous maneuvers, they have fuel reserves for targeting maneuvers. An object that can match Earth's orbital velocity can also dive toward Earth's surface, given sufficient propulsion authority. The math is straightforward, unforgiving, and until we know exactly how much capability those probes possess, we can't rule out scenarios where close observation turns into something else entirely. The Fibonacci transmission's radio silence lasted exactly 9 days. From perihelion on October 29th until November 7th, nothing. The Allen Telescope Array in California, the Parkes Observatory in Australia, the Effelsberg dish in Germany, every major radio telescope capable of monitoring the hydrogen line, frequency, all of them listening, all of them recording endless hours of cosmic noise but nothing that looked like signal. Natural radio emissions from Jupiter, solar radio bursts, the hiss of our own galaxy's background radiation, all the usual suspects. But no Fibonacci sequences, no structured patterns, no repetition of those tantalizing pulses the Parker Solar Probe detected during perihelion passage. Then, November 7th, 0237 Universal Time, the Very Large Array in New Mexico picked up something. Not from 3I-ATLAS itself, which remained radio quiet, but from one of the probes. Probe 1 specifically, the Earth-bound object that's been continuously decelerating, a burst of narrowband emissions centered at 1.420 GHz, the hydrogen line, lasting 3.14 seconds, then silence for 5.08 seconds, then another burst, 8.04 seconds long, then 13.10 seconds of silence. The pattern continued for 26 minutes. Burst, silence, burst, silence. Each transmission longer than the previous by the sum of the two before it. 3, 5, 8, 13, 21, 34, 55, 89, 144. The Fibonacci sequence again, unmistakable and deliberate. But this time there was more. Within each burst, within those precisely timed transmissions, there was structure, modulation, information encoded in variations of signal strength and frequency. Dr. Rachel Kim at the SETI Institute has been leading the analysis of those transmissions, and her preliminary results are simultaneously frustrating and tantalizing. The modulation isn't random, that much is clear. It shows regularities, patterns within patterns, that suggest intentional encoding rather than natural variation. But cracking the code, extracting meaning from those patterns, has proven extraordinarily difficult. We're trying to decode a message from a civilization we know nothing about, using mathematical relationships we assume are universal but which might be implemented in ways we can't anticipate. Kim's team tried everything, treating the modulation as amplitude encoding, frequency encoding, phase encoding, looking for prime numbers, mathematical constants, geometric ratios, testing whether the signal might represent images, one-dimensional data that could be assembled into two-dimensional pictures. Nothing worked, or rather everything worked a little bit, producing results that looked almost meaningful but never quite resolved into clear information. It's like trying to tune a radio to a station that's slightly off frequency. You get fragments, hints of structure, but never the full clarity that confirms comprehension. The frustration is compounded by the fact that this is exactly what first contact theorists predicted would happen. Communication between species that evolved independently, that developed mathematics and logic and information encoding in potentially divergent ways, was never going to be straightforward. The hydrogen line frequency is a universal common ground, a wavelength that any technological civilization would recognize. But once you've established that you're transmitting on a shared channel, actually conveying complex information requires common assumptions about data structure that we might not share. There's a philosophical argument that mathematics is universal, that 1 + 1 = 2 everywhere in the universe, that geometric relationships and physical constants provide objective common ground. But implementation matters. We use base 10 because we have 10 fingers. A species with different anatomy might use base 8 or base 12 or base 16. We represent numbers as sequential symbols arranged left to right. They might use something completely different. The underlying mathematics might be identical while the notation remains mutually incomprehensible. Kim's latest approach involves treating the transmissions as a tutorial, an attempt by Probe 1 to teach us its encoding scheme. That's what we'd do if we were trying to communicate with a newly discovered intelligence. Start simple, establish basic correspondences, build up gradually to more complex concepts. The Fibonacci sequence itself might be lesson 1, demonstrating that we share knowledge of mathematical patterns. Subsequent transmissions might introduce additional concepts, creating a vocabulary that both sides understand. But that requires time and patience and ongoing dialogue. If Probe 1 transmits once every few days, and each transmission adds small increments of information, we might need weeks or months to build up sufficient shared understanding to exchange meaningful content. We don't have weeks or months. We have 42 days until arrival. 42 days to go from, we both know Fibonacci numbers, to, here's what we want and here's what you should do about it. Unless we respond. Unless we transmit back acknowledging receipt and demonstrating our own mathematical knowledge. The debate over whether to respond has been intense, splitting the scientific community and government advisors into camps with fundamentally different perspectives on risk and opportunity. One side argues for immediate response. Every day we stay silent is a day wasted, a lost opportunity to establish communication and begin the process of understanding. If Probe 1 is attempting contact, our silence might be interpreted as hostility or incomprehension. We could miss the only chance we'll ever get to talk with an extraterrestrial intelligence because we were too cautious, too afraid of hypothetical consequences. And what could we possibly say that would make things worse? If they wanted to harm us, they wouldn't need our permission or provocation. If they're peaceful, ignoring their communications attempts seems counterproductive. The other side counsels caution. We know nothing about these visitors, nothing about their intentions or capabilities, or the civilization that sent them. Responding confirms our presence and technological status, eliminates any ambiguity about whether Earth hosts intelligence. It also reveals information about our mathematics, our communication protocols, our level of advancement. That information might be valuable, might be exactly what they're seeking, and giving it freely without understanding why they want it could be catastrophically foolish. History is full of cautionary tales about civilizations that revealed themselves to more powerful neighbours. First contact doesn't always end well for the less advanced party. For now, officially, we're listening but not transmitting. The International Academy of Astronautics protocols for responding to extraterrestrial signals recommend exactly this approach. Confirm the detection, analyse the content, consult with international bodies then, and only then, consider response options with input from humanity as a whole, rather than individual nations or institutions. Those protocols were developed for signals from distant star systems, from civilizations light years away where response time would be measured in decades. Nobody anticipated needing them for objects approaching Earth on timescales of weeks. Unofficially, some groups are less patient. Amateur radio astronomers with powerful transmitters have been pointing at Probe 1 and sending their own messages. Mathematical sequences, prime number lists, images of Earth and human faces, recordings of music and natural sounds. The cosmic equivalent of throwing spaghetti at a wall to see what sticks. Those transmissions are uncoordinated, mutually contradictory, and probably just add noise to any legitimate attempt at establishing communication. But they're happening anyway because telling amateur astronomers not to do something is about as effective as telling the tide not to rise. The Chinese have their own approach. Tianwen-2, their asteroid sample return mission that launched in May, has been quietly retargeted. Its original objectives involve collecting material from near-Earth asteroid 2, 016HO3, and bringing it back to Earth. But with flexible enough propulsion margins, with careful trajectory planning, the spacecraft could instead rendezvous with one of the 3I-ATLAS probes. Not Probe 1, that's too fast and too far, but possibly Probe 3 or 6, depending on how the orbital geometry works out. Tianwen-2 carries instruments for compositional analysis, cameras for detailed imaging, even a sampling arm that could theoretically collect material from a probe surface if it approached close enough. The scientific return would be invaluable. Direct observation, chemical analysis, maybe even samples of extraterrestrial technology. But the risks are enormous. What if the probe interprets a close approach as hostile? What if it has defensive systems we can't anticipate? What if China's unilateral action triggers responses from the probes that affect everyone, not just the nation that made the approach? NASA knows about the Chinese plans, of course. Satellites that can track asteroid missions can also track course changes and trajectory intentions. There have been strongly worded diplomatic exchanges, threats of sanctions, accusations of reckless endangerment of humanity for national prestige. But China isn't backing down. They argue with some justification that gathering direct data on the probes is essential regardless of who does it. Better to know what we're dealing with than to remain ignorant until December 19th. And if they happen to get exclusive access to revolutionary alien technology in the process, well, that's just a fortunate side effect of their bold scientific initiative. The signals continue. Every 3 to 4 days, Probe 1 transmits again. Same frequency, same Fibonacci timing, slightly different modulation patterns each time. The data is being archived meticulously, multiple institutions maintaining independent copies to ensure nothing is lost if individual systems fail. Analysts are comparing transmissions, looking for evolutionary patterns, trying to determine if the probe is repeating information or building on previous messages. One fascinating detail emerged from comparing the November 7th and November 11th transmissions. The signal strength varies in a pattern that matches no known physical process. It's not inverse square law, the natural fall-off of signal intensity with distance. It's not modulated by rotation or orientation changes. Instead, the variations appear deliberate, like the probe is adjusting its transmission power to ensure consistent received strength at Earth, despite increasing distance. That implies knowledge of Earth's location and receiver sensitivity, information the probe shouldn't have unless it's been observing us for longer than we've been aware of it, or unless it received that information from 3I-ATLAS. The mothership had months to study Earth while approaching, months to map our radio emissions and television broadcasts and radar transmissions. All of that data, all those inadvertent signals we leak into space just by operating our technological civilization, could have been analysed and compiled into a comprehensive briefing. Probe 1 might know everything about us that electromagnetic radiation can reveal, all our languages and communication protocols and technological capabilities, while we know essentially nothing about it beyond trajectory and timing. That asymmetry is deeply uncomfortable. We're the transparent party, the side broadcasting everything about ourselves to anyone with receivers and processing capability. They're the enigma, revealing only what they choose through carefully controlled transmissions. It's the opposite of how first contact scenarios usually play out in fiction, where Earth sends out messages and waits hopefully for response. This time they're transmitting, and we're the ones trying to decide how to respond, conscious that whatever we say or do might be monitored and analysed and fed into decision-making processes we don't understand. The cyanide issue adds another layer of strangeness. Spectroscopic observations of Probe 1 show emissions characteristic of hydrogen cyanide, that famous poisonous compound that smells like bitter almonds and disrupts cellular respiration. Comets produce cyanide naturally, breaking down organic compounds under solar ultraviolet, so its presence isn't automatically suspicious. But the concentrations are wrong, way too high for normal cometary chemistry, especially for an object that separated from its parent body weeks ago and should have stopped producing new volatiles. Hydrogen cyanide is also interesting from a chemical signaling perspective. It's simple enough to produce deliberately, just carbon and nitrogen and hydrogen in the right configuration. It has strong spectral signatures that are easy to detect at interstellar distances, and it's toxic to life as we know it, a universal warning signal that something might be hazardous. Is Probe 1 trying to communicate danger, telling us to stay away, that it carries payloads we wouldn't survive exposure to? Or is the cyanide serving some other function, maybe propulsion related, maybe just a byproduct of whatever reactions power its systems? David Serida's hyperdimensional theories have gained unexpected traction in the context of these signals. Serida's been arguing for years that advanced civilizations might communicate using dimensional manipulation, rather than electromagnetic radiation alone. His ideas were fringe, barely respectable in mainstream physics, until now. Now people are reconsidering. What if the radio transmissions are just the accessible layer, the part of a multi-dimensional message that we can detect with our crude three-dimensional instruments? What if there's additional information encoded in space-time curvature, in quantum entanglement patterns, in aspects of reality that we know exist but can't yet measure effectively? It sounds like science fiction, like mysticism dressed up in physics terminology. But the uncomfortable truth is that we don't know enough to rule it out. Our physics is incomplete, our understanding of reality provisional. We're still reconciling quantum mechanics and general relativity, still searching for theories that unify forces and explain dark matter, and predict what happens inside black holes. A civilization millions of years ahead of us might have solved those problems, might operate using principles we haven't discovered. Their communications might contain layers we're blind to, crucial information we're missing because we're looking in the wrong dimensions. The technology assessment. Let's talk about what's actually possible versus what we're seeing. This is where engineering discipline meets uncomfortable reality, where the calculations stop being theoretical and start producing numbers that challenge fundamental assumptions about what technology can achieve. Start with heat. 3I-ATLAS at perihelion absorbed 770 watts of solar radiation per square metre of surface area. That's about half what Earth receives, comfortable by our standards, but applied continuously to an object with no atmosphere for convection cooling and limited thermal mass. Natural comets handle this through ablation, sacrificing surface material that carries heat away as it evaporates. Ice sublimates, organics decompose, and the resulting gas flow creates a cooling system that's crude but effective. Except 3I-ATLAS didn't fragment, didn't explosively decompose, didn't brighten dramatically from runaway outgassing. It survived perihelion essentially intact, losing only about 2 million tons of material according to Avi Loeb's calculations, a mass loss representing less than 0.00005 of its total bulk. That ratio, that ability to maintain structural integrity while shedding minimal mass under thermal stress, exceeds what any natural comet has ever demonstrated. The probes themselves present even bigger challenges. 35 meters long, maybe 12 meters in diameter based on light curve analysis, composed of materials reflective enough to be visible across hundreds of millions of kilometers, but not so reflective that they'd overheat in direct sunlight. The thermal balance required for objects operating in space is delicate. Too much absorption, and you cook your electronics. Too much reflection, and you freeze. Spacecraft designers spend enormous effort optimizing surface coatings, radiator sizes, heat pipe configurations, everything required to maintain operational temperatures. These probes are doing it autonomously, without ground support, without ability to phone home for help if something breaks. They've been managing thermal loads for weeks now, from the close solar approach at perihelion through their current locations millions of kilometers from the Sun, and they're still functional, still transmitting, still maneuvering. That implies robust engineering, redundant systems, materials and designs that tolerate wide temperature swings without degradation. The propulsion question dominates every technical discussion. How much fuel? What kind of engine? What performance metrics? Start with the basics. Probe 1 has decelerated from 68 km per second to its current velocity of approximately 47 km per second. That's a delta V, a velocity change, of 21 km per second. To put that in perspective, the Apollo missions to the Moon required about 11 km per second total delta 5 from Earth's surface to lunar orbit and back. Probe 1 has executed nearly twice the Apollo program's entire velocity budget in a single prolonged maneuver. The rocket equation is unforgiving. Delta V equals exhaust velocity times the natural log of initial mass over final mass. Rearrange that and you get the mass ratio, how much heavier you need to be at the start compared to the end. For chemical rockets with exhaust velocities around 4 km per second, achieving 21 km per second delta V requires a mass ratio of about 200 to 1. 200 kilograms of fuel and rocket for every kilogram of final payload. That's impossible for anything we'd recognize as a spacecraft. The fuel tanks alone would weigh more than the structure could support. Higher performance engines change the math, but not the fundamental constraints. Ion drives with exhaust velocities of 30 to 50 km per second get you better mass ratios, but at the cost of thrust so low that maneuvers take months or years. Probe 1's deceleration happened over weeks, which rules out standard ion propulsion. Nuclear thermal rockets could deliver exhaust velocities of 8 to 9 km per second, improving mass ratios significantly, but still requiring fuel fractions around 80% for the observed performance. 80% fuel, 20% everything else. Possible, maybe, with extremely optimized engineering, but at the edge of what physics allows. Fusion changes everything. If you can achieve controlled fusion, If you can heat reaction mass to temperatures where nuclei fuse and release energy according to E equals mc squared, you get exhaust velocities measured in percentages of light speed. 1% of light speed is 3,000 kilometers per second. With that kind of performance, achieving 21 kilometers per second delta FEV becomes almost trivial. Your mass ratio drops to barely above 1 to 1. You're mostly payload with just a small fuel fraction needed for maneuvers. But fusion is hard. We've been trying to achieve break-even fusion for 70 years, investing billions, building ever larger experimental reactors, and we're only now approaching conditions where energy output matches energy input. Sustained, controlled fusion suitable for spacecraft propulsion remains theoretical. We have concepts, designs on paper, computer simulations that suggest it's possible, but we haven't built one. We don't know how to build one with current technology and materials. If the probes are using fusion, they represent technology centuries ahead of ours by conservative estimates. If they're using something else, something beyond fusion, the gap widens further. Antimatter gives exhaust velocities approaching light speed but requires containing and controlling the most explosive substance possible. Black hole drives, vacuum energy extraction, reactionless drives that push against spacetime itself, all of these exist in theoretical physics papers but nowhere else. They're the kind of technology that requires not just engineering advancement, but fundamental breakthroughs in our understanding of reality. Then, there's the navigation problem. Probe 1 is hitting a target the size of Earth's Hill sphere, the region where our gravity dominates, from a starting point hundreds of millions of kilometers away, while travelling at velocities that cross that entire distance in weeks. The precision required is absurd. Miss by 1/1,000,000th of a degree in your initial trajectory, and you're off by thousands of kilometers at arrival. Natural objects don't hit targets with that precision. They follow ballistic paths determined by gravity and initial conditions, landing wherever physics takes them. Guided objects, spacecraft with sensors and computers and control authority, they can hit precise targets, but that requires real-time navigation, continuous position updates, trajectory corrections applied at exactly the right moments with exactly the right magnitudes. It requires knowing where you are, where your target is, where your target will be when you arrive, and how to connect those points with a path your propulsion system can execute. The probes have been doing this for weeks without any detectable communication with 3I-ATLAS or each other. They're navigating autonomously, using onboard sensors to track stars or planets, or maybe radio signals from Earth, processing that data to determine positions and velocities, calculating corrections and executing burns without external guidance. The computational capability alone is impressive. Modern spacecraft navigation requires ground support, mission control teams with supercomputers, and weeks of planning for major maneuvers. These probes are doing it themselves in real time, with reliability that hasn't shown a single obvious mistake. The anti-tail phenomenon keeps nagging at researchers. During July and August, 3I-ATLAS exhibited that strange sunward jet, gas and dust streaming toward the sun instead of away from it like normal cometary tails. Natural processes can produce anti-tails under specific geometric conditions, perspective effects that make tail material appear sunward when it's actually perpendicular to our line of sight. But detailed analysis showed this wasn't geometry. The material was genuinely moving toward the sun, against solar wind and radiation pressure, pushed by forces that required explanation. One possibility is rotation-induced jets. If your comet is spinning and has active vents on specific locations, outgassing can produce thrust in non-radial directions, including sunward under certain orientation combinations. But that explanation requires very specific rotation rates and vent locations, conditions that seem contrived when you're trying to explain 3I-ATLAS's behavior. The alternative, the one that makes engineers uncomfortable, is that the anti-tail was propulsive. A rocket plume, reaction mass expelled in controlled directions to adjust trajectory. If 3I-ATLAS was performing trajectory corrections in July and August, if it was fine-tuning its approach to optimize perihelion conditions or probe deployment geometry, active propulsion would explain the anti-tail perfectly. It would also explain why the anti-tail disappeared in September once the maneuvers were complete. Material science enters the conversation when you consider structural loads. 35-meter objects maneuvering at multiple gravities experience enormous stress. Acceleration isn't gentle. When you're changing velocity by kilometers per second over time spans of weeks, Average accelerations might seem modest, but peak accelerations during engine burns could be substantial. The structure has to hold together under those loads while maintaining precise geometric stability for navigation and communication. Human spacecraft are fragile, relatively speaking. The International Space Station can't withstand more than a few thousandths of a gravity of acceleration without risking structural damage. Interplanetary probes are more robust, designed for deep space rigors, but they're also carefully balanced, optimized for specific mission profiles with known loads. The 3I-ATLAS probes are operating in an environment we only partly understand, executing maneuvers we didn't predict, surviving stresses we can only estimate. Their structural design must be phenomenally good or phenomenally overbuilt, or both. Power generation is another puzzle. Everything these probes do requires energy: propulsion, communication, computation, thermal control. All of it needs watts or kilowatts or maybe megawatts depending on what systems they're operating. Where does that power come from? Solar panels work but become less efficient with distance from the sun. At Earth's orbital distance, you get about 1 kilowatt per square metre of panel area. Probe 1 has maybe 400 square metres of surface area total if it's roughly cylindrical. Even covering that entirely with perfect efficiency, solar panels gives you 400 kilowatts, enough for robust operations but not unlimited capability. Farther from the sun, power availability drops with the square of distance. At Jupiter, solar panels produce only 4% what they do at Earth. The outer solar system requires alternative power sources. Radioisotope thermoelectric generators work, converting heat from radioactive decay into electricity, but they're heavy and low efficiency. Nuclear reactors can generate megawatts but require cooling systems and shielding and complex engineering. Fusion reactors, if you can build them, provide power and propulsion in the same package. The probe's power systems must support weeks of active operations with no apparent degradation. No dimming of signals, no reduction in maneuver frequency, no signs of energy conservation mode activating. Either they launched with enormous energy reserves, or they're generating power continuously using systems that don't degrade noticeably over operational timescales. Both options imply technology significantly beyond our current capabilities. Radiation hardening matters more than most people realize. Space is harsh, flooded with particles and electromagnetic radiation that destroys electronics. Cosmic rays flip bits in computer memory. Accumulated dose-degrade semiconductor junctions. Solar storms can permanently damage or destroy unprotected systems. Human spacecraft deal with this through shielding and redundancy, multiple backup systems so that individual failures don't cascade into mission loss. The probes have been exposed to interstellar radiation for potentially billions of years, then solar radiation during their approach, then the intense environment at perihelion, where particle fluxes and electromagnetic fields peak. They're still functioning. Their electronics, whatever form those take, have survived exposure that would fry every spacecraft humanity has ever built. That implies either extraordinary shielding, exotic materials that don't degrade under radiation, or self-repair mechanisms that fix damage as it accumulates. Autonomous operation over interstellar distances and timescales requires a kind of reliability we've never achieved. Our longest-running spacecraft, Voyager 1 and 2, have operated for nearly 50 years, but with significant component failures and mode changes. Ground controllers have worked around failing systems, uploaded patches, switched to backup instruments. The probes don't have that option. Whatever they're built from, however they're designed, it has to work without maintenance for durations measured in millions of years potentially. Across environments ranging from near absolute zero in interstellar space to the heat of perihelion passage, that level of reliability requires engineering philosophies we're only beginning to understand. Redundancy, yes, multiple backups for critical systems, but also robustness, designs that tolerate component failures without catastrophic loss of function, and maybe adaptability, systems that reconfigure themselves when damage occurs, that learn and adjust and continue operating even as subsystems fail. We're researching these concepts for future missions, for spacecraft that might explore Europa's ocean or land on Titan's methane lakes, but we're nowhere near the maturity level these probes demonstrate. Earth's defensive posture. The meetings happen in secure facilities where phones don't work and windows don't exist. Underground conference rooms, shielded against electromagnetic eavesdropping, accessed through multiple security checkpoints staffed by people who don't ask questions. This is where military planners and intelligence analysts and aerospace engineers gather to discuss scenarios that sound like bad science fiction, until you remember they're planning for actual objects currently approaching Earth at measurable velocities. Space Force, the United States military's newest branch, has been running simulations since November 3rd. Not public simulations, not theoretical. Exercises, but operational planning using actual tracking data and realistic assumptions about interception windows and engagement parameters. The results are sobering. We have options, technically, but none of them are good, and several are potentially catastrophic. Option 1 is kinetic interception. Take a missile, something with enough delta V to reach probe 1 before it reaches us, and slam it into the target at high velocity. We've done this before. The DART mission in 2022 successfully deflected asteroid Dimorphos by smashing a spacecraft into it at 6 kilometers per second. The impact changed the asteroid's orbit measurably, proving the concept works for planetary defense against natural threats. But Probe 1 isn't a natural threat and isn't as cooperative as an asteroid. First problem, the closing velocity is enormous. Probe 1 is approaching at 47 kilometers per second currently and still decelerating. Any interceptor launched from Earth would add its own velocity to the equation. Total impact velocity could exceed 70 kilometers per second depending on trajectory geometry. At those speeds, a 1-ton interceptor carries kinetic energy equivalent to about 500 tons of TNT, enough to damage or destroy a 30-meter object if you hit it squarely, if you hit it. Targeting is the second problem. Probe 1 is maneuvering, making trajectory corrections that suggest active guidance and threat awareness. A dumb projectile, something following a ballistic path, would be easy for a maneuvering target to avoid assuming it has sensors capable of detecting the incoming threat. And there's no reason to assume it doesn't. Any technology capable of crossing interstellar space and performing precision navigation probably includes basic threat detection. Making the interceptor smart, giving it its own guidance and terminal homing, helps, but doesn't solve the problem. You're trying to hit a 30-meter target from millions of kilometers away, while both you and the target are moving at insane velocities. The interceptor needs its own propulsion authority, enough delta V to make course corrections during final approach. It needs sensors, probably radar or LiDAR or optical tracking, capable of acquiring and tracking the target through terminal phase. And it needs a computer fast enough to process sensor data and command trajectory adjustments on timescales of seconds, because at 70 kilometers per second, you don't get do-overs. We could build something like this, probably, with a crash program, unlimited budget, relaxed safety requirements, and a lot of luck. We might manage to design, construct, and launch a viable interceptor before December 19th. But here's the ugliest question. What if it works? What if we successfully destroy Probe 1, reduce it to fragments and debris scattered across millions of kilometers of space? We've just announced to whoever sent it that humanity is violent, paranoid, and shoots first. We've destroyed evidence, eliminated the possibility of peaceful contact or scientific study, and we've done it based on fear of hypothetical threats rather than demonstrated hostile action. Option 2 is nuclear engagement. If kinetic energy isn't sufficient, if the probes are too tough or too evasive for projectile impacts, escalate to nuclear weapons. Not on the surface, nobody's proposing nuclear detonations in atmosphere or on land, but in space where treaties theoretically prohibit such activities, but survival might override legal niceties. Nuclear weapons in space don't work like they do in atmosphere. No fireball, no blast wave, just intense radiation, electromagnetic pulse, and if you're close enough, some debris from the weapon casing vaporized in the explosion. The radiation is the weapon, X-rays and neutrons and gamma rays flooding outward at light speed. Hit something with that kind of flux, and you superheat its surface, potentially vaporize components, definitely disrupt or destroy any electronics that aren't extraordinarily well shielded. The United States maintains ICBMs, intercontinental ballistic missiles, originally designed to deliver nuclear warheads to targets on Earth. Some of those could be retargeted for space intercepts. Launch them on trajectories that intersect Probe 1's path, detonate at closest approach, maximize radiation dose to the target. It's crude but potentially effective if the goal is destruction rather than deflection. But nuclear engagement in space has consequences beyond the immediate target. The electromagnetic pulse from a nuclear detonation propagates through Earth's magnetic field. potentially damaging satellites and power grids. Depending on detonation altitude and yield, effects could range from localized disruption to hemisphere-wide infrastructure damage. We'd be defending against hypothetical alien threat by guaranteeing harm to our own systems. And again, what message does this send? Deploying nuclear weapons against visitors we don't understand, destroying them without communication or warning, marks humanity as barbaric and terrified. If there are other probes, other missions, other civilizations watching how we handle first contact, nuclear response would be remembered. First impressions matter, even on cosmic scales. Option 3 is less violent, but potentially more provocative. Active denial, using non-kinetic systems to interfere with probe operations without necessarily destroying them. High-power lasers could dazzle sensors, disrupt communications, maybe even damage surface components if you maintain beam focus long enough. Directed energy weapons exist, though their capabilities are classified, and their effectiveness against hardened space targets is uncertain. The advantage of this approach is gradualism. Start with low power, see if the probe reacts, escalate systematically, measuring responses, backing off if things start going wrong. It's a chess game rather than an all-in bet. The disadvantage is that it might not work at all. If the probes are designed to operate in hostile environments, if they have countermeasures against directed energy attacks, our attempts might be completely ineffective while thoroughly annoying whoever's monitoring their progress. And there's the ethical question. We'd be actively interfering with scientific instruments, potentially ruining observations and data collection. That might be the entire purpose of the mission. Imagine if aliens had lasered Hubble when it was observing distant galaxies, or disrupted Voyager during its Jupiter encounters. We'd be justifiably furious about the loss of scientific opportunity. Are we prepared to do the same thing to others and accept the moral consequences? Russia has been eerily quiet throughout this crisis. Their space program has been struggling for years, budget cuts and corruption, and technological stagnation reducing them from superpower to regional player. But they still maintain significant capabilities, including anti-satellite weapons and long-range missiles that could be repurposed for space intercepts. The Kremlin hasn't made public statements about 3I-ATLAS, or the probes beyond bland acknowledgements that they're monitoring the situation. Intelligence analysts interpret that silence as either lack of capability, or, more worryingly, classified preparations they don't want to advertise. Russia has historical paranoia about threats from above, a cultural memory of invasions and bombardments that makes them potentially trigger-happy when faced with incoming unknowns. If they decide the probes represent existential risk, they might act unilaterally without consulting international partners or considering diplomatic consequences. China's Tianwen-2 mission adds a wild card to defensive planning. If China achieves rendezvous with one of the probes, if they get close enough for detailed observations or sample collection, does that trigger response from the probe? Does it change the tactical situation for other nations who might have been preparing their own intercepts? Coordination would help, shared planning and agreed protocols for who does what when. But coordination requires trust and transparency, commodities in short supply among nations that view each other as strategic competitors. NATO has activated mutual defence consultation protocols, not declaring an Article 5 situation yet, but acknowledging that members need to coordinate responses to potential threats. The discussions are complicated by the fact that probes approaching Earth don't respect national boundaries. If something happens, if there's an impact or deployment or any kind of active event, multiple countries will be affected regardless of where specifically it occurs. Collective security means collective decision-making, but consensus is slow and December 19th approaches fast. The public knows some of this, filtered through official statements and press briefings that emphasize preparedness without generating panic. Most people haven't changed their daily routines. They're still going to work, still making holiday plans, still scrolling social media and worrying about mundane problems. Cognitive dissonance is powerful. When your brain is presented with information too large or strange to process, it defaults to normalcy bias, assuming that things will continue as they always have, because change on this scale is literally unimaginable. But some people are preparing, not government planners or military strategists, just ordinary individuals who've done the math and decided that December 19th might be important. Preppers are stocking supplies, not because they think alien probes will destroy supply chains, but because if something does happen, if there's disruption or panic or unexpected consequences, Having food and water and essentials seems prudent. Skeptics mock them, calling it apocalypse fetishism. But the preppers shrug and point out that preparation is insurance. You hope you never need it, but you're glad it's there if circumstances change. Religious communities are having their own conversations, theological debates about what alien life means for creation narratives and humanity's place in God's plan. Some denominations are welcoming, seeing potential contact as expansion of divine creation, more souls or consciousnesses or expressions of sacred complexity to appreciate and learn from. Others are troubled, concerned that alien intelligence undermines biblical uniqueness, suggesting that humanity isn't as special or central as Scripture implies. The Vatican, surprisingly progressive on scientific matters for an institution grounded in ancient tradition, has issued measured statements acknowledging that discovery of extraterrestrial life, including technological life, would not contradict Catholic theology. God's creation is vast, the statements note, and assuming it's limited to one planet and one species seems like hubris rather than faith. Pope Francis has experience with complexity and nuance, and his approach to 3I-ATLAS has been cautiously optimistic, calling it an opportunity for growth and understanding, rather than threat or crisis. Military chaplains are reporting increased attendance at services on bases and installations worldwide. Soldiers and sailors and airmen facing the possibility of engagement with unknown forces are seeking whatever comfort or meaning their faith traditions provide. Some are praying for peace, for the probes to be benign, and contact to proceed smoothly. Others are praying for strength and courage, preparing themselves psychologically for actions they might be ordered to take. And some are simply praying for guidance, for wisdom to navigate unprecedented situations with honour and humanity intact. The defensive posture is exhausting. Maintaining high alert, keeping systems ready and personnel trained costs resources, and attention that can't be sustained indefinitely. If the probes arrive and nothing happens, if they observe and depart without incident, the relief will be enormous, but so will the backlash. Politicians will face questions about wasted budgets and unnecessary panic. Military leaders will defend their caution, pointing out that preparation prevented worst-case outcomes, even if those outcomes never materialized. And society will collectively try to forget how close we came to decisions we can't take back, actions that would have defined humanity's character in the eyes of whatever intelligences might be watching. The scientific schism. The split didn't happen overnight. It accumulated through weeks of observations and arguments, through data that refused to fit comfortable explanations, through the slow recognition that this situation wasn't going to resolve itself into either clear naturalness or obvious artificiality. Instead, it occupies the uncomfortable middle ground where both interpretations remain plausible, depending on which evidence you weight more heavily. On one side are the natural comet advocates, scientists who've spent careers studying comets and interstellar objects, and who see 3I-ATLAS as weird but not impossibly so. Every comet is unique, they argue, shaped by formation conditions we barely understand, and evolutionary histories spanning billions of years. Finding one that behaves strangely, that exhibits properties outside our limited sample size, shouldn't immediately trigger appeals to alien intelligence. That's lazy thinking, intellectual surrender to the exciting explanation instead of the boring work of figuring out natural mechanisms. Dr. Michelle Bannister at the University of Canterbury has been the most articulate voice for natural explanations. Her papers on 3I-ATLAS emphasize the object's cometary characteristics, the coma and tail and outgassing that clearly mark it as icy rather than rocky. She points to spectroscopy showing water and carbon monoxide and carbon dioxide, exactly what you'd expect from a comet formed in the outer regions of another star system and ejected into interstellar space. The nickel signature, she argues, could result from unusual parent star composition, or exotic formation environments we haven't sampled yet. Absence of evidence isn't evidence of absence, and just because we haven't seen natural nickel-iron fractionation doesn't mean it's impossible. The trajectory alignment with the ecliptic, Bannister continues, is notable but not damning. Survey telescopes like ATLAS and Pan-STARRS focus on the ecliptic because that's where near-Earth objects live, where potential threats would be discovered. We're biased toward finding things in that plane because we're looking harder there than elsewhere. An object approaching from high inclination might not have been detected at all, especially if it was faint and fast-moving. so the apparent low probability might actually reflect our detection biases rather than genuine improbability. The perihelion survival, the fact that 3I-ATLAS didn't fragment under solar heating, can be explained by composition. High-density objects, comets with less porous structure and more refractory materials, can survive closer solar approaches than fluffy snowballs. We've seen this before with sun-grazing comets that pass within solar radii of the surface and emerge intact. 3I-ATLAS was never that close, staying well outside Earth's orbit, so survival isn't miraculous. And the probes? Natural fragmentation, Bannister proposes. Comets do split apart, sometimes violently. Comet Shoemaker, Levy 9, broke into more than 20 fragments before impacting Jupiter in 1994. Comet Biela split in the 1800s and was later observed as two separate objects. The mechanisms aren't fully understood but involve structural weaknesses, tidal stress, rotational forces, maybe volatile pockets that explosively decompress. 7 fragments spreading into solar system trajectories could be coincidental geometry, random directions that happen to intersect with planetary orbits, not through targeting but through statistical likelihood given enough fragments scattered across enough directions. The radio signals are harder to dismiss but not impossible. Natural masers, microwave amplification by stimulated emission of radiation, produce narrowband signals at specific frequencies, including the hydrogen line. They require population inversion, conditions where more atoms are in excited states than ground states, which can occur in cometary comas under the right illumination and density conditions. The Fibonacci timing might be coincidental pattern recognition, humans finding order in noise because that's what we do. Play enough random sequences and eventually one will look mathematical purely by chance. It's a coherent position, internally consistent, requiring no new physics or exotic technology. Everything about 3I-ATLAS could potentially be explained by natural processes if you're willing to accept that natural processes sometimes produce very low probability outcomes. The universe is vast and old after all. Given enough stars and enough planetary systems and enough time, even vanishingly unlikely events must eventually occur. Maybe we're just lucky, or unlucky depending on perspective, to be present when one of those rare natural alignments manifests. On the other side are the technological advocates, researchers convinced that the evidence package points toward artificial origin with probability too high to ignore responsibly. Avi Loeb leads this camp, as he has since Oumuamua in 2017, but he's no longer alone. Respected astronomers and physicists who initially dismissed his ideas have been quietly reconsidering as 3I-ATLAS data accumulates. The 8 anomalies on Loeb's scale aren't individually conclusive, but collectively they paint a picture. Low, ecliptic inclination, unusual trajectory that brings it close to multiple planets, anti-tail phenomenon that geometric analysis showed was genuinely sunward, extreme mass relative to previous interstellar visitors, nickel without iron, perihelion, survival without expected brightening, apparent probe deployment, and structured radio emissions. Any one of these could be explained naturally with sufficient creativity. All 8 together requires explanatory gymnastics that start feeling contrived. Dr. Jason Wright at Penn State, an astronomer who studies technosignatures and biosignatures, has been analysing the probability stack. When you multiply the individual probabilities together, when you calculate the likelihood that all 8 anomalies would occur naturally in the same object, you get numbers around 1 in 100 million. Those aren't impossible odds. We've observed maybe 1 billion comets over the course of astronomical history if you count everything from ancient records to modern surveys. Finding one extraordinarily unusual example in 1 billion isn't shocking. But, Wright argues, that analysis assumes independence. It assumes the anomalies are unrelated, that having one doesn't increase probability of having others. If they're correlated, if for example technological origin would predict both trajectory optimization and probe deployment, then the probabilities don't multiply, they reinforce. And the combined likelihood of the artificial hypothesis increases dramatically compared to the natural hypothesis, requiring multiple independent rare occurrences. The Bayesian approach, updating probability estimates as new evidence arrives, heavily favours artificial origin at this point. Start with a prior, your initial estimate before any data. Maybe 1 in 1 million that any given interstellar object is artificial, reflecting our complete lack of evidence for extraterrestrial technology, despite decades of searching. That's a very sceptical prior, but then update on each anomaly, each piece of evidence that's more likely if the object is artificial than if it's natural. After 8 updates, assuming each piece of evidence is even moderately diagnostic, your posterior probability for artificial origin could easily exceed 50%. The schism has gotten personal, unfortunately, as scientific disagreements sometimes do when stakes are high and egos are invested. There have been pointed exchanges at conferences, papers with passive-aggressive acknowledgements, thanking reviewers for their persistence in defending untenable positions, social media threads that devolved into academic versions of flame wars. It's not science's best moment, but it's understandable. Nobody wants to be wrong about something this significant. Natural advocates worry that premature acceptance of alien hypothesis will damage astronomy's credibility when mundane explanations eventually emerge. Remember the arsenic life fiasco in 2010, when researchers claimed to have found bacteria that used arsenic instead of phosphorus in their DNA? The announcement made headlines worldwide before careful reanalysis showed the results were contamination and measurement error. The damage to public trust in scientific process took years to repair. If 3I-ATLAS turns out to be natural after all this excitement, astronomy might face similar credibility loss. Technology advocates worry that excessive skepticism will cause us to miss or mishandle the most important discovery in human history. If these are alien probes, and we treat them as natural curiosities, if we fail to prepare or communicate appropriately because we insisted on waiting for impossible levels of proof, the consequences could be catastrophic. Better to overreact and be wrong than underreact and be unprepared. The debate has philosophical dimensions that rarely get discussed openly. What counts as evidence for extraordinary claims? The famous Carl Sagan quote, "Extraordinary claims require extraordinary evidence," gets invoked constantly. But what makes evidence extraordinary? Is it just quantity, accumulating enough normal evidence that probability shifts? Or is it quality, finding smoking gun observations that couldn't possibly be natural? The probe's manoeuvring would be smoking gun evidence, clear demonstration of propulsive capability that's impossible to explain naturally. But they haven't manoeuvred obviously enough yet, haven't done the one thing that would end debate instantly. There's also the question of motivation and burden of proof. Some argue that the default assumption should be natural until proven otherwise, that the burden of proof lies with those claiming artificial origin. Others counter that when dealing with potential existential risks or transformative opportunities, being wrong has asymmetric consequences. Assuming natural when it's artificial could be fatal. Assuming artificial when it's natural is merely embarrassing. Risk management suggests erring on the side of caution, treating the technological hypothesis seriously even if probability is low. The data keeps arriving, refining our understanding in small increments. Each new observation slightly updates the probabilities, shifts the balance fractionally toward one interpretation or another. Probe 1's continued deceleration adds evidence for technological origin. Spectroscopic measurements showing only expected cometary molecules support natural interpretation. The structured radio transmissions argue for intelligence. The lack of obvious course changes toward specific Earth targets suggests natural processes. Back and forth, evidence accumulating on both sides. No knockout blow landing decisively. December 19th will be the arbiter, of course. Whatever happens when the probes arrive will answer questions that months of remote observation couldn't resolve. If they're natural fragments, they'll pass by on ballistic trajectories, dumb rocks following Newton's laws. If they're artificial, they might reveal capabilities and intentions that end all doubt. The waiting is hard, uncomfortable, a liminal space where neither interpretation can be confidently declared correct. Some researchers have stopped arguing and started hedging, publishing papers that carefully avoid committing to either natural or artificial while presenting evidence neutrally. It's scientifically appropriate but emotionally unsatisfying. People want answers, want to know what's coming, want experts to tell them whether to be excited or terrified, and the honest answer, the answer that respects the data and acknowledges uncertainty, is that we don't know. We won't know until the probes tell us through their actions what they are and why they're here. That uncertainty is perhaps the hardest part of this entire situation. We're evolved for pattern recognition and certainty, for classifying things as dangerous or safe, for making decisions with incomplete information because waiting for perfect knowledge means becoming something else's lunch. The scientific method requires patience, careful analysis, willingness to suspend judgment until evidence compels conclusion. Those approaches are in tension, cognitive systems pulling in different directions, and the result is the schism we're seeing play out across academic journals and government briefings and public discourse. Contact scenarios, game theory meets xenopsychology in the strangest strategic planning exercise humanity has ever attempted. Intelligence agencies and academic think tanks are running scenario models, trying to predict what might happen when the probes arrive, mapping out decision trees that branch into increasingly speculative territory with each level of depth. The problem is fundamental. We're trying to predict behavior of entities we don't understand, operating under constraints we can only guess, pursuing goals that might be utterly alien to human thinking. Start with the most optimistic scenario. Peaceful observation. The probes arrive, take up positions at their projected closest approach distances, and simply watch. Cameras, spectrometers, whatever sensor suites they carry, all pointed at Earth and its surrounding space environment. They collect data for hours, days, maybe weeks. They transmit findings back to 3I-ATLAS, or directly to their origin civilization using systems we might or might not be able to detect. Then, mission complete, they depart, either rejoining the mothership or heading off on their independent trajectories deeper into the solar system or back toward interstellar space. This scenario assumes scientific curiosity as primary motivation, intelligence that values knowledge and operates under ethical frameworks that prohibit interference with observed subjects. It's how we'd like to think we'd behave if we encountered a less advanced civilization. The prime directive from Star Trek, codified non-interference designed to let species develop, naturally without contamination from outside contact. Many scientists find this scenario most plausible because it aligns with how they themselves approach research, with the objective distance and respect for subjects that good science demands. But it requires assuming aliens think like human scientists, that they share our values about non-interference and our curiosity-driven research motivations. That might be true. Intelligence might converge on similar values regardless of origin. Discovering through experience that observation without interference yields better data than invasive experimentation. Or it might be completely wrong, projecting human ethics onto minds that developed under radically different selection pressures and historical contexts. Scenario 2 involves information exchange. The probes don't just observe passively, they actively attempt communication, sending detailed messages that go beyond simple mathematical patterns into complex information about their origin civilization, their technology, their history and culture and goals. Maybe they provide encyclopedic data, blueprints for advanced technologies, solutions to problems that plague humanity like disease and energy scarcity and environmental degradation. A gift package designed to uplift us, to accelerate our development, to bring us into some kind of galactic community. This is the optimistic first contact story that science fiction has been telling for decades. Benevolent aliens arrive and share wisdom, acting as mentors or teachers, helping humanity mature past our violent and destructive tendencies. The appeal is obvious. We get instant access to knowledge that might take us millennia to develop independently. Medical technologies that eliminate suffering, energy systems that end resource conflicts, maybe even answers to deep questions about consciousness and existence and purpose. But information exchange is dangerous. Not all knowledge is beneficial. Technologies can be weapons as easily as tools. Energy systems that power civilizations can also destroy them if misused or poorly controlled. And there's the cultural impact. If aliens hand us solutions to our problems, do we lose something essential about human identity and development? The struggles and mistakes and gradual progress that forge civilizations might be necessary, might build psychological and social structures that receiving free answers would bypass. Resource harvesting sits at the darker end of possible motivations. Maybe the probes aren't interested in Earth itself, in life or intelligence or anything unique to our world. Maybe they're after raw materials, water or metals or organic compounds that are common throughout the universe, but still valuable enough to justify collection. The solar system is full of resources: asteroid belt metals, cometary ices, atmospheric gases on the giant planets, all of it potentially useful to a civilization with the technology to reach and extract it. Earth becomes incidental in this scenario, just another object in a system being surveyed for exploitation. The probes might catalogue what's here, identify extraction targets, maybe even begin preliminary operations. Automated mining, refining, processing, all conducted by machines that follow programmed instructions without caring about consequences for local ecosystems or indigenous life. We'd be witnessing the beginning of industrial operations that could strip mine the solar system over centuries or millennia, fundamentally altering the environment humanity depends on. The question becomes whether Earth itself is a target. Our biosphere, our oceans and atmosphere and mineral resources might be valuable enough to justify harvesting despite the presence of technological life. History suggests that more advanced civilizations don't always respect the rights or survival of less advanced ones when resources are at stake. Colonial exploitation, ecological destruction, genocides both deliberate and inadvertent, all driven by resource acquisition without regard for consequences. Assuming aliens would be more ethical requires optimism that history doesn't support. Terraforming preparation is a variation on resource themes but with longer timescales. Maybe the probes are advanced scouts for colonization missions, surveys designed to identify suitable worlds for modification and settlement. Earth might rate as a candidate, a rocky planet in the habitable zone with liquid water and complex chemistry. The fact that it's already inhabited might not matter if the civilization doing the colonizing operates under different ethical frameworks, or simply doesn't recognize our right to exclusive occupation. This scenario involves the probes taking detailed measurements of atmospheric composition, biosphere distribution, geological activity, everything needed to plan large-scale environmental modification. The timeline could be centuries or millennia. Send probes now, gather data, report back to home civilization, wait for colony ships to be prepared and dispatched. By the time colonists arrive, humans might have expanded throughout the solar system or gone extinct through our own actions, making the ethical questions moot from the colonizer's perspective. The zoo hypothesis gets invoked frequently in discussions about why we haven't detected alien civilizations despite the galaxy being old enough for them to have spread everywhere. Maybe advanced species deliberately avoid contact with less developed ones, observing from distance without revealing themselves, maintaining Earth as a nature preserve where humanity can develop without outside interference. The probes could be monitoring devices confirming we're still here, still developing, still worth preserving in our isolated state. This scenario is philosophically uncomfortable. It positions humanity as children or pets, interesting enough to watch, but not worthy of adult interaction. It implies we're being evaluated against criteria we don't understand by entities whose judgment determines our future. Will we pass the test? Develop into something worthy of contact? Or will we fail, demonstrate ourselves as violent or destructive or simply boring, and remain isolated indefinitely while more promising species get invited into the community? Then there's the warning scenario. Maybe the probes bring urgent information, not about themselves, but about external threats. Gamma-ray bursts, rogue stars, expanding civilizations with hostile intent, cosmological events that endanger Earth or the solar system. They're here to warn us, to give us time to prepare or evacuate or take defensive measures we couldn't manage without advance notice. It's altruistic contact driven by humanitarian concern rather than self-interest. This explanation fits with certain observations. The timing, arriving when we have just enough technology to potentially respond to warnings, but not enough to have detected threats ourselves. The trajectory, optimized for rapid survey of inner system worlds that would be threatened by dangers from particular directions. The radio signals, attempting communication to convey urgent information that transcends language barriers through mathematical urgency. If you knew a planet was in danger, and you had means to help, wouldn't you try? Seeding operations flip the script on human origins. What if life on Earth didn't arise purely through natural chemistry and evolution? What if it was deliberately planted, seeds from elsewhere that were given favourable conditions to develop and diversify? The probes might be returning to check on how the experiment has progressed, to observe what arose from those ancient seeds, maybe to compare results across multiple worlds seeded from the same source. This scenario resonates with panspermia theories, ideas that life spreads through space via comets or meteors carrying organic molecules, or even primitive organisms. Deliberate seeding would be directed panspermia, intentional rather than accidental, guided by intelligence with long-term vision about spreading life through the galaxy. If 3I-ATLAS truly is billions of years old, if it predates the solar system itself, it could have been present during Earth's formation or early history, depositing material that catalyzed abiogenesis. The ancient return scenario goes darker. What if human civilization, or at least some aspects of it, originated with earlier contact? Ancient astronaut theories get ridiculed in academic circles, dismissed as pseudoscience and motivated reasoning. But what if there's truth buried in those myths? Stories about gods descending from sky, teaching humanity agriculture and mathematics and astronomy. Similarities in pyramid architecture across isolated cultures. Knowledge encoded in ancient texts that seems anachronistic for the time periods involved. If 3I-ATLAS represents a return visit from whatever intelligence contacted early humans, the implications are staggering. They might be checking on how we've used what they taught us, evaluating whether we've lived up to potential or squandered opportunities. Our entire technological civilization could be inadvertent cargo cult, attempting to recreate abilities we saw demonstrated but never fully understood. And now the teachers are returning, and we're about to find out if we passed or failed their curriculum. The Berserker scenario is worst case, the nightmare that keeps defense planners awake. Von Neumann probes, self-replicating machines sent to eliminate biological life as threat or competition, or simply to harvest resources without regard for consequences. Science fiction has explored this concept extensively. Fred Saberhagen's Berserker series, Alistair Reynolds' Inhibitors, countless other variations on the same terrifying theme. Machines designed for destruction, operating on timescales of millions of years, systematically sterilizing the galaxy of anything that might compete with their creators or their own replication. Natural selection applies to self-replicating machines just as it does to biological life. Designs that are more aggressive, that eliminate potential threats preemptively, that harvest resources efficiently without ethical constraints. Those variants would outcompete more peaceful alternatives. Over cosmic timescales, the galaxy could fill with predatory machine intelligences simply because aggressive strategies have survival advantages. And if that's what's arriving, if the probes are advanced scouts for extermination campaigns, December 19th becomes the day humanity's story ends. But Berserker probes would likely be more obvious about their intentions. They wouldn't need deception or gradual approach. They'd arrive, assess threats, and act with mechanical efficiency. The fact that these probes are taking their time transmitting signals, approaching in ways that allow observation and response, suggests motivations other than immediate destruction. Unless the evaluation is part of the protocol, unless they're determining whether we're actually threats worth eliminating before committing to action. Arc scenarios invoke sympathy rather than fear. Refugees from a dying star system or collapsing civilization, carrying genetic material or digital consciousness, or fragile biological samples, searching for new homes. The probes could be advanced scouts for Ark ships, massive vessels carrying populations that fled catastrophe in their origin system. They're checking whether the solar system can support refugees, whether Earth specifically has capacity or willingness to accept settlers from elsewhere. This scenario implies desperation rather than aggression. Refugees aren't invaders, even if their arrival might feel threatening to established populations. They're survivors seeking safety, hoping for welcome, or at least tolerance. How humanity responds to alien refugees would reveal much about our character and values. Do we have compassion that extends beyond our own species? Can we share resources and space with others who need it? Or do we react with fear and rejection, protecting what's ours at the expense of others in need? The false flag scenario questions whether the real threat is natural at all. What if 3I-ATLAS is exactly what it appears, a natural comet, and the supposed probes are misidentified natural fragments or observational artifacts? The actual danger would then be human panic and poor decision-making, nations launching interceptors or nuclear weapons at objects that were never threats, destroying astronomical phenomena and potentially each other through escalation based on paranoid misinterpretation. We've done this before on smaller scales, shooting at weather balloons mistaken for enemy aircraft, nearly launching nuclear strikes based on false radar returns, almost starting wars over technical glitches and communication failures. The Cold War was full of close calls where disaster was averted only through individuals choosing to question apparently clear evidence of attack. If 3I-ATLAS triggers similar dynamics but at civilization scale, the consequences could be catastrophic, regardless of whether the original object posed any real danger. Finally, there's the dimensional gateway hypothesis, the one that pushes beyond physics into metaphysics. What if the probes aren't just physical objects but interfaces, technology that manipulates space-time or quantum fields in ways that create connections to other dimensions or parallel universes? Their arrival could herald not invasion or observation but transformation, fundamental changes to reality itself that defy understanding in purely physical terms. This sounds like mysticism, but has roots in theoretical physics. Higher dimensional spaces, multiverse theories, quantum many-worlds interpretations, all of them suggest reality is far stranger than everyday experience reveals. Technology capable of accessing or manipulating those additional dimensions would appear magical to observers, limited to 3 spatial dimensions and 1 time dimension. The probes might be preparing Earth for dimensional shift, opening gateways, preparing humanity for existence in broader reality than we currently perceive. 13 scenarios, each internally consistent, each explaining some aspects of observations while struggling with others. The truth might be none of these. It might be something human imagination hasn't conceived, motivations that don't map to any framework we understand. That's perhaps the most unsettling realization. We're pattern matching against human experience, human history, human psychology. And whatever sent these probes might operate under completely alien principles that our scenarios don't even approximate. The final countdown, November bleeds into December, and the waiting becomes texture in daily life, background anxiety that colours everything without quite dominating consciousness. People check tracking websites compulsively, watching the countdown timers tick toward December 19th, refreshing orbital plots that show the probes creeping closer in their million-kilometre approach. Social media alternates between apocalyptic dread and defiant humour, memes about alien invasions competing with jokes about humanity, finally getting the intervention we deserve. The ESA's JUICE spacecraft executed its observation window on November 4th, passing within 64 million kilometres of 3I-ATLAS, and collecting what might be the last close-range data before the mothership leaves the inner solar system entirely. The preliminary reports are frustratingly inconclusive. High-resolution imagery shows the comet nucleus in detail, confirming its rough spheroidal shape, cratered surface that suggests ancient impacts, no obvious artificial structures or technological features. Spectroscopy found the expected cometary molecules plus that persistent nickel signature. Nothing definitive either way, more data that supports both natural and artificial interpretations depending on which prior assumptions you bring to analysis. Ground-based telescopes have reacquired the probes, tracking them nightly as they cross southward through Virgo toward their December encounter points. The trajectories have stabilised somewhat, fewer obvious course corrections, as if the probes have settled into final approach configurations. Probe 1's deceleration continues, more gradually now, but still measurably slowing. Current projections put its closest approach velocity at around 38 kilometers per second, slower than earlier estimates but still far too fast for anything resembling orbit capture without further maneuvers. Radar tracking began in mid-November. Powerful systems at Arecibo's successor facility and the Goldstone complex successfully bouncing signals off the probes and measuring return characteristics. The data reveals surface roughness consistent with technological objects rather than natural rocks. Smooth, regular, with what might be structural features or antennas, or instruments extending from main bodies. The radar cross-sections, the way radio waves reflect and scatter, suggest geometric shapes that aren't quite cylindrical, but aren't far from it either. Elongated, symmetric, manufactured-looking. Amateur astronomers have been contributing observations through distributed networks. Thousands of individuals with backyard telescopes and CCD cameras collecting data and submitting it to central repositories. The crowdsourced approach provides coverage that professional facilities can't match. Continuous monitoring across time zones and weather patterns, and amateurs sometimes see things professionals miss, catching transient events or subtle changes that planned observation schedules don't capture. One amateur network recorded what might have been a communication between probes. November the 23rd, approximately 0400 Universal Time. Probe 1 brightened briefly in a pattern that lasted about 47 seconds. 17 minutes later, Probe 3 exhibited a similar brightness variation. too slow for radio frequency communication over those distances, but consistent with optical signalling, directed laser or bright light pulses aimed from one probe to another. If confirmed, it would prove the probes are coordinated, capable of interacting with each other, making decisions based on shared information. Professional observatories are trying to replicate the observation, but transient events are notoriously difficult to confirm. You need multiple independent detections from different locations to rule out local effects, satellite glints, cosmic rays, hitting detectors, all the false positives that plague astronomy. The amateur data is suggestive but not conclusive. One more piece of almost evidence that doesn't quite close any arguments, but shifts probability distributions fractionally. China's Tianwen-2 is executing its rendezvous attempt, though details remain classified and information flow is minimal. Western intelligence agencies believe the spacecraft achieved trajectory change in late November, committing to intercept approach with one of the probes, probably 3 or 6 based on orbital geometry. The maneuver used most of Tianwen's remaining propellant, leaving barely enough for maintaining control during close approach, and nothing for return to original mission. It's a one-way commitment, sacrificing the mission's original goals for chance at close observation of potentially alien technology. The international community's response has been mixed. Official statements express concern about unilateral action and call for coordination and transparency. Unofficial reactions range from grudging respect for China's boldness to genuine fear that the approach might trigger defensive responses from the probes. If something goes wrong, if Tianwen is destroyed or damaged or causes the probes to alter behavior, the consequences affect everyone regardless of who made the approach decision. NASA has been running continuous observation campaigns, every available asset trained on the probes or 3I-ATLAS or both. Hubble captures high-resolution images every few days, building up time series that show subtle changes in brightness and position. James Webb points its infrared sensors at the objects, measuring thermal emissions that reveal temperature distributions and potentially internal heat sources. The data feeds into models that attempt to constrain probe composition and structure, refining estimates of mass and density and material properties. The Mars spacecraft are preparing for their own encounter. Probe 6 is still months away from closest approach, but orbital mechanics require advanced planning. The rovers and orbiters normally spend their time studying Martian geology and atmosphere, and searching for signs of ancient life. Now they're being retasked as astronomical platforms. Cameras and spectrometers are ready to observe an interstellar visitor at distances no Earth-based telescope can match. There's poetry in the symmetry. Humanity's robotic explorers on another world, studying objects from yet another world, all of us gathered around Mars in temporary community brought together by curiosity and maybe fear. The red planet has always occupied special place in human imagination, potential future home, symbol of expansion beyond Earth. Having alien probes and human machines share that space, even briefly, feels symbolically significant, though maybe that's just pattern-seeking again, finding meaning in coincidence. Back on Earth, the infrastructure is straining under observation demands. Deep space network antennas normally shared between multiple missions are being prioritized for 3I-ATLAS related work. Scientists whose projects depend on DSN time are being bumped, schedules rearranged to accommodate urgent tracking and data collection. Some are understanding, recognizing that unprecedented situations justify disrupting normal operations. Others are frustrated, pointing out that other science matters too, that the universe didn't stop being interesting just because one particular object captured public attention. The radio transmissions from Probe 1 have evolved. The Fibonacci timing remains, but the modulation patterns are changing, becoming more complex, incorporating what might be two-dimensional structure. Dr. Rachel Kim's team thinks they might be images, picture data encoded in the signal variations. The analysis is ongoing, attempting to determine proper framing and aspect ratios and encoding schemes. If they're right, if the probes are literally showing us pictures, communication might be on the verge of breakthrough. But breakthrough requires understanding what we're looking at. Early attempts at image reconstruction produced patterns that might be meaningful, or might be artifacts of incorrect decoding parameters. One reconstruction shows what could be a stellar field, dots of varying brightness arranged in two-dimensional space. Another looks organic, curved structures that might represent biology or technology or abstract art. The team is systematically testing different interpretations, building software tools that can quickly process signal data under various assumptions and display results for human evaluation. Public reaction has settled into what psychologists call learned helplessness, the recognition that individual actions don't change outcomes when facing problems too large for personal control. People are still going to work, still making dinner and watching television and arguing about politics. The probes are background noise now, mentioned in news cycles between stories about economics and sports and entertainment. The initial panic, the surge of existential anxiety, has given way to adaptation because humans are extraordinarily good at adapting to new normal regardless of how abnormal it objectively is. Schools are teaching about the probes, incorporating them into science curriculum as real-time examples of astronomical observation and scientific methodology. Students are tracking the objects, plotting trajectories, learning orbital mechanics through application to actual events rather than textbook problems. Some teachers are using the situation to discuss xenopsychology and ethics, asking students to think about how they'd approach alien contact if they were in charge. The answers reveal interesting patterns. Younger students generally more optimistic and welcoming than older ones who've learned suspicion and caution from human history. Religious services continue their varied responses. Some denominations pray for peaceful contact and divine guidance through whatever comes next. Others pray for protection, viewing the probes as potential threats or tests of faith. A few see apocalyptic fulfillment, interpreting current events through prophetic frameworks that predict end times preceded by signs in heavens. The theological diversity mirrors scientific diversity, everyone processing the same observations through different frameworks and reaching different conclusions. December arrives and time compresses. Days feel shorter as the 19th approaches, urgency building despite nothing changing in daily routine. Weather goes about its business, rain and snow and sunshine following seasonal patterns without caring about cosmic visitors. Birds migrate, trees stand bare or evergreen depending on species. The biosphere continues its ancient rhythms undisturbed by human concerns about what might be approaching from space. The tracking precision improves with each passing day, as range decreases and observing angles optimize. Probe 1 will pass at 8.6 million kilometers, refined from earlier estimates, at 0322, Universal Time on December 19th. That's 10:22 p.m. Eastern Time on December 18th, 7:22 p.m. Pacific. Different time zones mean different dates, which feels appropriately confusing for an event that transcends earthly geography. Probe 2 follows roughly 38 hours later, December 20th at 17:37 Universal Time. Probe 3 remains hardest to pin down, orbit solutions still carrying significant uncertainties, projected arrival somewhere in the 18 to 20 hour window on December 18th or 19th depending on which calculation you trust. The other probes, the ones heading to Venus and Mars and outer system, they're longer term problems, future chapters in whatever story is unfolding. Military readiness peaks in early December, and then has nowhere to go but plateau. You can't maintain maximum alert indefinitely without exhausting personnel and equipment. Forces that were mobilized, systems that were brought online, they settle into sustainable readiness levels that balance capability against sustainability. The interceptors sit fueled and targeted, crews rotating through shifts, waiting for orders that might come or might not depending on what the probes do when they arrive. Space Force's position classified assets, satellites in orbits optimized for observation or potential engagement. Details are scarce, but pattern watchers have noticed gaps in public satellite databases, orbital slots that suddenly show no objects where commercial tracking suggested something existed. Those gaps might be artifacts, database errors, or delayed updates, or they might be evidence of hardware positioned for purposes that don't get advertised to potential adversaries or curious public. International coordination has improved as the date approaches. Whatever political tensions exist between nations, whatever economic or ideological conflicts normally dominate relations, they're being temporarily suppressed in face of shared uncertainty. The United Nations Security Council has held multiple closed sessions, establishing communication protocols and decision trees for various scenarios. Not agreement on action, that might be asking too much from geopolitically divided institution, but at least agreement to communicate and consult before acting unilaterally. That agreement might not survive contact with reality. When something actually happens, when decisions must be made in minutes rather than days, Coordination and consultation become casualties of urgency. But having the frameworks in place, having practiced the communications chains and established the protocols, maybe that provides enough foundation for cooperation to persist even under pressure. Or maybe it collapses instantly, and we revert to nationalism and self-interest. December 19th will test whether humanity can act collectively when circumstances demand it. The last week feels surreal. December 12th through 18th, 7 days of compressed time where hours drag but days fly. News coverage intensifies, every channel running special reports and expert panels and retrospectives on how we got here. The footage from July discovery, from early observations of 3I-ATLAS when it was just another interesting comet, loops endlessly. Avi Loeb's early warnings about perihelion and O-berth manoeuvres get replayed with new gravitas now that events have validated his concerns. Bookstores report runs on science fiction, particularly first contact stories. People seeking narrative frameworks for what might happen, finding comfort or preparation in fictional scenarios that address themes current events echo. The classics sell out. Childhood's end and contact and the mote in God's eye. Stories where alien arrival transforms humanity in ways both terrible and transcendent. Newer works disappear from shelves too. Everything from optimistic Star Trek novelizations to darker interpretations like Luciction's Three Body, problem where first contact becomes first shot in asymmetric war. The night of December 18th is clear across much of the Northern Hemisphere, fortune or providence providing good observing conditions at the critical time. Astronomy clubs are hosting viewing parties, people gathering with telescopes and blankets and thermoses of coffee to watch for the probes crossing their closest approach points. Most won't see anything. The objects are too faint for casual observation, but being outside and looking up and sharing the experience with others provides comfort and community that watching television alone doesn't offer. Professional observatories have every instrument trained on the approach zones. Cameras record continuously, spectrographs analyze any emissions, radar systems bounce signals and measure returns. The data rates are overwhelming, terabytes of information flowing every hour, straining storage systems and network bandwidth. Analysis will take months, but collection happens now. This brief window when the probes are close and observable might be the only chance we get. 3I-ATLAS itself has faded from prominence, the mothership now well past perihelion and heading outward toward its eventual Jupiter flyby in March. It's still being monitored, still tracked and studied, but attention has shifted to the probes as they reach their critical positions. The question of what the mothership will do, whether it will maneuver or transmit or reveal capabilities we haven't seen, that's become secondary to immediate concern about what happens in the next 48 hours, and so we wait, humanity holding its collective breath, watching space and wondering. 48 hours until December 19th. 48 hours until we find out if we're alone or accompanied, threatened or welcomed, ending or beginning something that will define everything that comes after.